Welcome. Tonight, we're going to do something that no human being was ever able to do before the age of science. We're going to travel backward in time, not in a machine, not through a wormhole or a portal or any device that fiction has ever imagined. We're going to travel backward through the language of physics, through the accumulated observations of millions of scientists across centuries of patient, careful, wonder-driven work. We're going to travel backward through 13.8 billion years of cosmic history and arrive together at the very beginning of everything. Not the beginning of Earth, not the beginning of our solar system or our galaxy, the beginning of the universe itself, the moment before which there was no before, the event from which all of space, all of time, all of matter, all of energy, all of the laws of physics that govern the falling of every leaf and the shining of every star, the moment from which all of this emerged. We're going to the Big Bang, and I want you to understand something before we begin, something that I think is easy to say but very difficult to truly feel in the body, in the quiet dark of wherever you are right now. The Big Bang is not a theory in the casual sense of the word. The way we sometimes use theory to mean a guess, an educated hunch, an idea someone had that might or might not be right. The Big Bang is the most comprehensively tested, observationally confirmed, mathematically precise account of cosmic origins that the human mind has ever produced. The evidence for it comes from so many independent directions, from the redshift of distant galaxies, from the existence and precise temperature of the cosmic microwave background radiation, from the measured abundances of hydrogen and helium and lithium in the oldest stars, from the observed large-scale structure of the universe, that dismissing it would require dismissing essentially everything we know about physics, chemistry, and astronomy simultaneously. It happened. We know this with extraordinary confidence. What we are doing tonight is not speculation. We are not imagining. We are narrating history, the deepest history, the history that contains all other histories inside it, the way an ocean contains every wave that has ever crossed its surface. And we're going to take it slowly. We have 3 hours together, you and I, and every one of those hours will be filled with ideas that I hope will settle gently into you like the slow accumulation of stars in a forming galaxy, each one small and dim by itself, but together, in aggregate, brightening the entire night. But first, if you're enjoying these long, slow journeys into the deep night of science, take a moment now, if it is not too much trouble, to like this video and subscribe to this channel. It costs you nothing but a gesture, and it means everything to those of us who make these things, who sit at desks in quiet rooms, trying to find the right words to describe things that were never meant to have words, because they happened before there were minds to make them. And leave a comment, please. Tell me where in the world you are right now. Tell me what time it is. Tell me whether it is raining or clear, whether you're in a city bright with artificial light or somewhere truly dark where the stars are visible through your window. I read every one of those comments, and I find them extraordinary, this small map of the world that assembles itself in the comments section of a video about cosmology, people listening from their bedrooms in Manila and their kitchens in Sao Paulo and their offices in Oslo, and their cars parked on quiet streets and places I have never been and never will go. You are all, every one of you, made of the same stardust we will be discussing tonight. And that connection, that shared atomic ancestry, is one of the genuinely lovely truths that cosmology has given us. Now, let's prepare. If you have not already done so, find your most comfortable position. Let your body settle into whatever shape feels most natural, most restful. Perhaps you're lying on your back with your arms at your sides, or curled slightly on one side with a pillow tucked against your chest, or stretched out flat with the weight of the blanket pressing gently and evenly across you. Whatever position you have found, let it be the one. Stop adjusting. Stop shifting. Give your body permission to be still. Dim the lights, or turn them off completely if you can. Darkness is important tonight. We're going to be talking about light, about the first light that ever existed, about light that was born when the universe was a fraction of a second old and has been traveling ever since. But to truly appreciate light, you must be willing to sit with the dark for a while. If you have a fan, or a white noise machine, or the sound of rain through a window, let those sounds be present. They are good companions for this kind of journey. They create a kind of acoustic cocoon around you, a soft boundary between the world inside this narration and the world outside it. And they will help your mind loosen its grip on the ordinary, the immediate, the particular, and open instead to the vast. Take a breath. Not a dramatic, deliberate, therapeutic breath. Just a breath. The kind you were already going to take. But notice it this time. Notice the air moving in through your nose or your mouth, filling your lungs, expanding your chest or your belly. Notice the brief pause at the top of the breath. And in the long, slow release, the quiet return, the body settling back. You just completed one of the most ancient cycles in the universe. The exchange of gases between a living organism and its atmosphere. An act performed by life on this planet for nearly 4 billion years, by creatures ranging from the first single-celled organisms in the primordial ocean to the enormous breathing apparatus of the blue whale. You are part of that chain. You're doing what life does. You are, in the most literal and biological and chemical sense, part of the story we are about to tell. Because the oxygen you just inhaled was forged in dying stars. The nitrogen that makes up most of what you breathed was scattered into the galaxy by ancient supernovae. The carbon dioxide you exhaled contains carbon atoms that were once part of other living things, other bodies, other moments of being alive on this small rocky planet. You are made of the Big Bang, and tonight we go back to find out how that happened. Before we descend into the deep past, I want to give you a sense of the distances we will be traveling tonight, because without that sense, the story risks feeling abstract, like numbers on a page rather than the staggering physical reality that it is. The universe is approximately 13.8 billion years old. Written out, that is 13,800 million years. If you were to compress that entire span of time into a single calendar year, with the Big Bang occurring at the first stroke of midnight on January 1st, then the first stars would not appear until late January. The Milky Way galaxy would form in February. Our own solar system, our sun and its planets, would not form until early September. Life on Earth would appear in September. The dinosaurs would not exist until Christmas. Modern humans, Homo sapiens, would not appear until the last few seconds of December 31st. All of recorded human history, every empire and revolution and invention and discovery, everything that has ever been written down or remembered or passed from one generation to the next, would occur in the final fraction of the final second of the final minute of the final day of this compressed cosmic year. That is the scale of what we are working with tonight. And yet, despite this almost incomprehensible depth of time, we can describe what happened in the first seconds, the first microseconds, the first unimaginably tiny fractions of a second after the Big Bang, with extraordinary mathematical precision. We have equations. We have observations. We have particle accelerators that recreate, in miniature, the conditions of those first moments. The deep past is not hidden from us. It is written into the structure of everything that exists. We just have to learn how to read it. Let's begin. Close your eyes for a moment, if they're not already closed, and try to imagine nothing, not darkness. Darkness is something. Darkness is the absence of light in a space that still exists, a volume that could, in principle, contain things but currently does not. Darkness presupposes space, and space, as we will discover tonight, is not nothing. Space is something extraordinary, something with structure and geometry and the capacity to expand and curve and vibrate. Space came into being at the Big Bang. Before the Big Bang, there was no space, not silence. Silence is the absence of sound in a medium that could carry it. Sound requires air or water or some material through which pressure waves can propagate. Silence presupposes a medium, and mediums are made of matter. Matter came into being at the Big Bang. Before the Big Bang, there was no matter, not cold. Cold is the absence of thermal energy in a system that exists and has a temperature. Cold is a state that matter can be in. But before the Big Bang, there was no matter to be cold. Not even time. Time, this is perhaps the hardest one. This steady, relentless, apparently universal arrow that carries everything from the past toward the future. This thing you feel so intimately in the ticking of a clock or the aging of a face or the simple fact of one moment following another. Time itself is not fundamental. Time is part of the universe. Time began at the Big Bang. Before the Big Bang, there was no before. This is the concept that, more than any other in cosmology, resists ordinary understanding. We are so thoroughly embedded in time, so completely constituted by it, that imagining its absence feels like trying to see your own eyes without a mirror. Every thought you have exists in time. Every sentence unfolds in time. The very act of imagining requires time, requires one moment after another in which the imagination can operate. And yet the physics tells us, with calm and patient insistence, that time had a beginning, that there was a first moment, that the question what happened before the Big Bang is, in the strict physical sense, not a meaningful question. It is like asking what is north of the North Pole. The question uses grammatically correct words, but refers to something that does not exist within the framework of the universe as we understand it. This is where we begin tonight, not with an explosion, not with fire and light. We begin with the question of nothing, because without sitting with that question for a moment, without feeling the full weight and strangeness of it, the Big Bang itself risks feeling like just another event in a sequence, rather than what it actually was. The origin of the sequence itself. The general theory of relativity, the mathematical framework developed by Albert Einstein in 1915 that describes gravity as the curvature of space-time, predicts that if you run the expansion of the universe backward in time, all of space, all of matter, all of energy converges to a single point, a singularity, a mathematical location where density becomes infinite, where temperature becomes infinite, where the curvature of space-time becomes infinite. Infinite, not very large, not larger than any number you can think of. Infinite in the strict mathematical sense, meaning the equations break down, divide by zero, produce results that have no physical meaning within the framework of the theory itself. This singularity is what we colloquially call the moment of the Big Bang. But physicists are quick to note something important. The singularity is not a thing that the theory predicts. It is a place where the theory stops working. It is the boundary of our current understanding, the edge of the map where the cartographers of physics have written, "Here our equations fail." This failure is not a sign that the Big Bang did not happen. It is a sign that at the extreme conditions present at the very beginning of the universe, general relativity is not the complete story. At the scales and energies of the Big Bang's first moments, quantum mechanics, the physics of the very small, becomes important. And we do not yet have a complete theory that combines quantum mechanics with general relativity, a theory of quantum gravity that could tell us what happens at the singularity itself. This is one of the great outstanding problems of theoretical physics. The search for quantum gravity, for a theory that can describe the universe at the Planck scale, the scale at which quantum effects and gravitational effects are equally important, is one of the most active and difficult frontiers of modern science. String theory, loop quantum gravity, causal set theory, these are all attempts to find this deeper framework. None has yet been confirmed by experiment. So we must be honest. There is a wall, a boundary in our knowledge, a place before which, or rather before, when we cannot currently see with the precision we would like. The first approximately 10 to the power of negative 43 seconds of cosmic history, the Planck epoch, remains beyond the reach of our current theories. It is the one chapter of the universe's history that we cannot yet read with confidence. But here is what is remarkable. Beyond that wall, even a fraction of a second after it, the story becomes describable, testable, precise, and we will go there together very soon. There is a question that every thoughtful person eventually asks when confronted with the Big Bang. It is a question that feels simple and is in fact one of the deepest in all of philosophy and physics. Why is there something rather than nothing? Or more specifically, where did all this come from? The matter, the energy, the laws of physics themselves. If there was truly nothing before the Big Bang, no space, no time, no matter, no energy, then how did the Big Bang happen? What caused it? And who or what, if anything, lit the fuse? These are real questions that physicists take seriously. And while they do not yet have complete answers, they have made remarkable progress toward framing the problem in ways that are, surprisingly, not entirely discouraging. The key insight comes from quantum mechanics, and it is this. At the quantum level, nothing does not stay nothing. In quantum field theory, the most precise physical framework ever developed, even a perfect vacuum, even a region of space containing no particles, no radiation, no matter of any kind, is not truly empty. The vacuum seethes with activity. Virtual particles, pairs of matter and antimatter, constantly flicker into existence and annihilate each other, appearing and disappearing so rapidly that they never violate the conservation of energy in any measurable way. This is not a theoretical construct invented to solve a problem. It is a measured, observed, experimentally confirmed physical reality. The Casimir effect, the Lamb shift in hydrogen spectral lines, the anomalous magnetic moment of the electron, all of these precisely measured phenomena confirm that the quantum vacuum is alive with this constant, fluctuating, invisible activity. The vacuum is not empty. The vacuum is restless. Some physicists, most notably Stephen Hawking and James Hartle, and later Lawrence Krauss, have proposed that the universe itself could have emerged from a quantum fluctuation. That the laws of quantum mechanics, applied to the vacuum, actually permit, or even require, that a universe can come into existence spontaneously, without a prior cause in the classical sense, through a process somewhat analogous to the spontaneous appearance of virtual particles from the quantum vacuum. This is known as the Hartle-Hawking no-boundary proposal, and also by the more popular, if slightly imprecise, phrase, a universe from nothing. The idea, stated simply, is that the universe has no boundary in imaginary time, that if you describe the geometry of space-time using a mathematical technique called Wick rotation, the universe has no beginning, no singularity, no edge. It is finite but unbounded, the way the surface of the Earth is finite but has no edges, no point at which it suddenly stops and gives way to non-existence. In this picture, asking what happened before the Big Bang is like asking what is south of the South Pole. The question is grammatically sensible but physically undefined. There is no before. Time, along with space and everything else, simply began. Not because something caused it, not because a force acted on some pre-existing material, but because the laws of quantum physics, in their deepest formulation, permit existence, may even demand it. This is philosophy at the edge of physics. These ideas are not yet confirmed. They may never be confirmable in the conventional experimental sense because they concern conditions that are not reproducible in any laboratory. But they're not mere speculation either. They are serious mathematical frameworks developed by some of the most careful minds in science, attempting to give a physically rigorous account of the deepest possible question. Why is there something? Perhaps because nothing, in the quantum sense, is unstable. Perhaps because the laws of mathematics and physics themselves have a kind of logical necessity that makes some form of existence more probable than pure absence. Perhaps because the question, ultimately, carries a hidden assumption that existence requires a cause, and perhaps that assumption is wrong. We do not know, and that not knowing is not a failure. It is the frontier, is the edge of the map where the territory is still being explored. But even if we accept, tentatively and with appropriate humility, that the universe could have emerged from a quantum vacuum, another question immediately presents itself, a question that many find even more vertiginous than the first. Where did the laws of physics come from? The quantum vacuum that seethes and fluctuates does so according to specific, precise, mathematical rules. The laws of quantum field theory. Those laws have a particular structure. They involve specific constants, specific relationships between quantities, specific symmetries and broken symmetries that determine how particles interact, how forces operate, how the vacuum itself behaves. These laws are extraordinarily finely tuned, in the sense that if you were to alter them even slightly, to change the strength of the strong nuclear force by a few percent, or the mass of the electron by a small factor, or the value of the cosmological constant by a tiny amount, the universe that resulted would be dramatically different, would likely contain no stars, no chemistry, no planets, and no life. The laws of physics are not arbitrary. They have specific values that make complexity possible, that make us possible. And the question of why they have these values, rather than some other set of values, is a question that physics cannot currently answer from within itself. Some physicists invoke the anthropic principle. We observe these laws because if the laws were different, we would not be here to observe them. This is logically correct, but feels, to many, unsatisfying. It explains why we observe fine-tuned laws without explaining why fine-tuned laws exist at all. Others invoke the multiverse, the idea that our universe is one of an enormous or infinite number of universes, each with different laws, different constants, different physical structures, and that we find ourselves in one compatible with our existence simply because the others did not produce observers. This is a serious scientific hypothesis, not a fantasy, but it is also currently untestable, and its status as science rather than philosophy is itself debated. Others still believe that the laws of physics are not contingent but necessary, that mathematics itself has a kind of existence independent of any particular universe, and that the physical universe is, in some sense, a mathematical structure, one that was always going to exist because the mathematics that describes it is necessarily true. We do not know the answer to this question. We may never know. And there's a certain quiet beauty in that admission, a beauty that is easy to miss if you're looking for the universe to provide neat resolutions rather than deeper mysteries. The universe does not owe us comprehension. It does not owe us answers. It simply is. And the fact that we are here, made of its matter, powered by its energy, governed by its laws, and curious enough to ask about our own origins, is itself one of the most extraordinary things about it. Let us approach the beginning as closely as our current physics allows. The Planck time. This is the smallest, meaningful unit of time in physics. It is approximately 5.4 times 10 to the power of negative 44 seconds. Written as a decimal, it is 0, followed by a decimal point, followed by 43 zeros, followed by the digits 54. It is a span of time so brief that no experiment we have ever devised, and no experiment we can currently imagine devising, could measure it or resolve events within it. At the Planck time, according to general relativity, the entire observable universe, everything that will eventually become the hundreds of billions of galaxies we can see with our telescopes, was compressed into a volume smaller than an atomic nucleus at a temperature and density so extreme that the four fundamental forces of nature, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, were unified into a single force. The universe had not yet had time to differentiate, to become varied, to develop the rich structure of forces and particles that we observe today. It was, in whatever sense the word can be applied to such conditions, simple. One thing, one unified state of reality, one undifferentiated something from which everything else would eventually emerge. At the Planck time, our map ends. Our equations fail. The territory beyond it, the first Planck time itself, and whatever preceded it, remains dark to us. But a fraction of a second later, everything changes. The universe begins to cool. The unified force begins to separate. Particles begin to form. Space begins to expand. The story of the universe, in all its staggering complexity and beauty, begins to unfold. And that is where we will go in the next chapter. But not yet. For now, simply rest with the idea of the beginning. Feel the weight of it, the strangeness of it, the almost indescribable fact that there's a question here at all, that the universe exists, that it has structure, that it follows laws, that it contains, after 13 billion years of cooling and expanding and collapsing and burning, creatures capable of sitting in the dark and wondering where they came from. You're the universe wondering about itself. That is not a metaphor. It is a physical fact stated in a different register. The atoms that make up your brain were forged in stars. The energy driving every neuron was ultimately released by nuclear reactions in the core of the sun, which was itself ignited by the gravitational collapse of a cloud of gas that was itself composed of hydrogen, created in the first 3 minutes after the Big Bang. The entire chain of causation that produced this moment, this thought, this wondering, traces back through billions of years to the very beginning we are discussing tonight. You did not come into the universe. You came out of it, the way a wave comes out of the ocean, or a thought comes out of a mind, or light comes out of a fire. You are not separate from the origin. You are a late expression of it, a local elaboration, a temporary and improbable and quite wonderful arrangement of Big Bang matter that has, against extraordinary odds, become aware of its own origins. Let that sit for a moment. There is no hurry tonight. The universe waited 13.8 billion years to have this conversation. A few more minutes of quiet will not change anything. Before we move into the heat and fire of the early universe in the next chapter, I want to pause and say something about evidence, about how we know what we know. Because the story of the Big Bang is sometimes presented as if it were a narrative constructed from imagination, a story someone made up about what might have happened, dressed up in the language of mathematics to give it an air of authority. This is not what it is. The Big Bang model is the conclusion of multiple independent lines of observational evidence, each one capable of standing on its own, each one pointing to the same picture of cosmic origins. The first line of evidence comes from the expansion of the universe. In the 1920s, the astronomer Edwin Hubble, working at the Mount Wilson Observatory in California, made a discovery that changed our understanding of the cosmos permanently. He found that distant galaxies are moving away from us. And not just away from us, but away from each other. The universe is expanding. Every galaxy, measured carefully, shows a redshift in its light, a stretching of the wavelengths of photons that indicates the source is receding. And the farther away the galaxy is, the faster it is receding. This is Hubble's law, and what it implies is straightforward. If the universe is currently expanding, then in the past it was smaller. Run the expansion backward long enough, and everything converges. Everything was once much closer together, much denser, much hotter. The second line of evidence comes from the cosmic microwave background radiation. In 1964, two radio astronomers at Bell Labs in New Jersey, Arno Penzias and Robert Wilson, were trying to calibrate a sensitive radio antenna and kept detecting a faint, persistent hiss of microwave radiation coming uniformly from every direction in the sky. They tried everything to eliminate it. They removed the pigeon droppings from inside the antenna. They checked their equipment repeatedly. The hiss would not go away. What they had accidentally discovered was the afterglow of the Big Bang itself. The cosmic microwave background, or CMB, is the light released when the universe was approximately 380,000 years old, light that has been traveling through the expanding universe ever since, cooling and redshifting as space expanded around it. Until today, it fills the entire sky as a bath of microwave radiation at a temperature of approximately 2.7 degrees above absolute zero. This radiation is extraordinarily precisely characterized. Its temperature, its spectrum, the tiny variations in its intensity from one direction to another, all of these have been measured with extraordinary precision by a succession of satellite missions, from COBE to WMAP to Planck. And every measurement is consistent to a remarkable degree of precision with the predictions of the Big Bang model. The third line of evidence comes from the abundances of light elements. The Big Bang model predicts that in the first few minutes after the Big Bang, when the universe was hot and dense enough for nuclear reactions to occur, specific quantities of hydrogen, helium, deuterium, and lithium should have been synthesized. The model predicts these abundances with precision. And when astronomers measure the chemical composition of the oldest stars, stars formed before any significant amount of stellar nucleosynthesis could have altered the primordial mix, they find these exact abundances. The universe's chemistry matches the model's predictions. The hydrogen and helium in the oldest stars are in exactly the ratio the Big Bang predicts. These three lines of evidence, the expansion of the universe, the cosmic microwave background, and the primordial element abundances, are the pillars on which the Big Bang model rests. They are not guesses. They are not inferences from first principles. They are measurements, direct observations of the universe that agree with a precision that would have seemed miraculous to any scientist a century ago, with the predictions of a model built on the physics of general relativity and quantum field theory. The Big Bang happened. We know this the way we know that the Earth orbits the Sun, or that DNA carries genetic information, or that the continents have moved across the surface of our planet over millions of years. Not with absolute philosophical certainty, because science does not deal in absolute certainty, but with the kind of practical certainty that comes from multiple independent observations, all pointing to the same conclusion. This is the foundation we stand on tonight. Solid ground, evidence-built ground, ground that extends back through 13 billion years of cosmic history to the hot, dense, unimaginably energetic origin of everything. Let your breathing slow a little more now. Notice that the room around you, whatever room you are in, is profoundly quiet compared to what we are about to describe. The temperature around you is perhaps 20 degrees Celsius, perhaps a little more or less. The air pressure is roughly 1 atmosphere. These conditions are so mild, so gentle, so extraordinarily far from the conditions of the early universe that it is almost impossible to hold the contrast in mind. In the first second after the Big Bang, the temperature of the universe was billions of degrees. In the first microsecond, it was trillions. In the first billionth of a second, it was a quadrillion degrees, a number so large that no analogy from daily life comes close to capturing it. The sun's core, hot enough to drive nuclear fusion for billions of years, is a mild and comfortable 15 million degrees. The early universe was hotter than the sun's core by a factor of billions upon billions. And yet, from that fire, from that almost incomprehensible furnace of energy and density, everything we see around us was born. The chair or bed you are lying in, the atoms of your body, the photons from the stars, the gravitational forces holding galaxies together. All of it, every last particle and wave and force and structure in the observable universe, traces its origin to those first seconds. In the next chapter, we go into that fire. For now, though, rest here for a moment, at the edge of the beginning, in the quiet space between the question and the answer, in the pause that the universe itself seemed to take before the extraordinary business of becoming everything began. The fire comes next, but the pause is worth something too. The pause is where the wondering lives. Imagine, if you can, a moment. Not a moment in the ordinary sense, not the kind of moment you experience as a pause between one thought and the next, not the kind of moment you might describe as fleeting or brief or gone before you noticed it. Imagine a moment so small, so almost incomprehensibly compressed in duration, that the entire history of human civilization, all 10,000 years of it, from the first scratch marks in Mesopotamian clay to the satellites and telescopes and particle accelerators of the present day, would fit inside it not once, not 1,000 times, not 1,000,000,000 times, but a number of times so enormous it would take more digits to write it than there are atoms in your body. That is the first second after the Big Bang. The first second is not a single event. It is a cascade, a waterfall, a furious and relentless sequence of transformations, each one of which, by itself, would constitute one of the most dramatic events in the history of the cosmos. Within the first second, the universe went from an undifferentiated plasma of unimaginable energy to a place containing the fundamental building blocks of all matter. It went from a state of complete, featureless uniformity to a place where the seeds of everything, every star, every galaxy, every atom in your body were already being planted. The first second is where the universe found its shape. Let's walk through it together, slowly, carefully, with the attention it deserves. We begin at the Planck time, 10 to the power of negative 43 seconds. A number so small it defeats intuition entirely. At this moment, the entire observable universe, the region of space that will eventually contain hundreds of billions of galaxies, was compressed into a volume smaller than a single proton. The temperature was approximately 10 to the power of 32 degrees Kelvin. The density was 10 to the power of 97 kilograms per cubic meter. These numbers are not meant to be grasped in the way you grasp the temperature outside or the distance to the nearest town. They are meant to be felt in the way you feel the edge of a cliff by standing close enough to look down without falling. They're the outer boundary of a territory so extreme that the ordinary landscape of physical intuition becomes completely useless. At the Planck epoch, as we discussed in the previous chapter, our current physics reaches its limit. General relativity and quantum mechanics both apply here, but they give contradictory answers when applied simultaneously, and we do not yet have the unified theory of quantum gravity that would reconcile them. The Planck epoch is the locked room of cosmology. We know it exists. We know something extraordinary happened inside it, but we cannot yet open the door. What we can say is this. At the Planck time, the four fundamental forces of nature were unified: gravity, electromagnetism, the strong nuclear force that holds atomic nuclei together, and the weak nuclear force responsible for certain kinds of radioactive decay. All four were a single force. There are no distinctions between them. The universe was symmetric in a deep and total way that it will never be again. And then it began to cool, because expansion, even at those extraordinary densities, meant cooling. And cooling meant change. The first separation happened at approximately 10 to the negative 36 seconds. This is still an almost incomprehensibly small fraction of a second, but it is several orders of magnitude larger than the Planck time. And at this scale, our physics begins to be able to say something meaningful. At this moment, gravity separated from the other three forces. It became distinct. The single unified force that had governed the Planck epoch split into two: gravity on one side and a still unified electroweak strong force on the other. This separation is called the Grand Unification Transition, and it marks the first differentiation in the history of the universe. The universe took its first step away from perfect uniformity. Think about what this means. Before this moment, there was no difference between the force that holds galaxies together and the force that holds protons together inside an atomic nucleus. They were the same thing. After this moment, they were not. The universe became, for the first time, a place with multiple kinds of interactions, multiple kinds of forces, a place with variety. Variety is the beginning of everything interesting. Also occurring at approximately this epoch, according to most versions of the theory, is one of the most extraordinary events in the history of the universe. An event called cosmic inflation. We will return to inflation in much greater depth later in our journey. But I want to introduce it here because it is woven into the story of the first second so deeply that it cannot be left out. Inflation is the name given to a proposed period of extraordinarily rapid expansion of the universe that is believed to have occurred at around 10 to the negative 36 seconds, lasting until perhaps 10 to the negative 32 seconds. During this period, the universe is thought to have expanded by a factor of at least 10 to the 26th power and possibly much more in an incredibly brief span of time. This expansion was not the gentle, steady expansion that the universe has been doing ever since. It was an exponential acceleration, driven by a form of energy embedded in the quantum vacuum that caused the universe to double in size again and again and again in rapid, relentless succession. To give you a sense of the scale, if a single proton inflated by the same factor, it would end up larger than the observable universe. Inflation, if it occurred, solves several deep puzzles about the universe we observe today, puzzles concerning why the universe looks so uniform in all directions, why it appears to be geometrically flat, and why there are no exotic relics from the early universe scattered through the sky. It stretches tiny quantum fluctuations in the primordial energy field to cosmological scales, turning the microscopic randomness of the quantum vacuum into the large-scale structure of the universe, the seeds from which galaxies and galaxy clusters will eventually grow. We will return to all of this. For now, hold it lightly. Inflation is the moment the universe took a single quantum breath and became, in that breath, vast. After inflation ends, the universe is filled with a dense, hot plasma of energy. The temperature is still extraordinary, perhaps 10 to the 20th degrees Kelvin. Space is expanding and cooling rapidly, and the forces of nature continue their process of differentiation. At approximately 10 to the negative 12 seconds, a temperature of roughly 10 to the 15th degrees Kelvin, a second great separation occurs. The electroweak force, which had remained unified since the Grand Unification Transition, splits into two. Electromagnetism separates from the weak nuclear force. They become distinct. They begin to behave differently. They begin to interact with matter differently. This transition is mediated by a mechanism called the Higgs mechanism, associated with a particle called the Higgs boson. The Higgs boson, famously detected at the Large Hadron Collider at CERN in 2012, is the quantum of a field that permeates all of space. When the electroweak symmetry breaks at this transition, certain particles, the W and Z bosons that carry the weak force, acquire mass through their interaction with the Higgs field. Other particles, the photons that carry electromagnetism, remain massless. This distinction between massive and massless force carriers is one of the most important structural features of the universe. It determines the range of forces, their strengths at different energies, the way they interact with matter. The universe, in acquiring a Higgs field, acquired one of its most fundamental characteristics. The electroweak epoch is the era we understand best among the very early moments of the universe. The physics of this era is precisely described by what physicists call the Standard Model of particle physics, a theoretical framework developed in the 1960s and 1970s and confirmed by experiment with extraordinary precision. We have built particle accelerators, machines of tremendous scale and engineering sophistication, specifically to recreate the conditions of this era and test our understanding of it. And the tests have passed. The Standard Model is one of the most precisely confirmed theories in the history of science. We were there, in a sense. We built machines to go back. From the electroweak transition onward, the universe enters a phase described by the Standard Model of particle physics, and here our knowledge becomes increasingly precise. The universe is now filled with a dense, hot plasma, a sea of elementary particles interacting at extraordinary rates. Among these particles are quarks, the fundamental constituents of protons and neutrons and gluons, the particles that carry the strong nuclear force and bind quarks together. At these temperatures, the energy of the thermal environment is so high that quarks cannot be permanently bound together. They exist in a free, roaming state, interacting constantly, forming briefly bound combinations and then separating again. This state of matter is called the quark-gluon plasma. It does not exist anywhere in the universe today under natural conditions, with one possible exception: the cores of neutron stars, where densities approach those of the early universe. But it has been created briefly and in miniature in experiments at the Relativistic Heavy Ion Collider at Brookhaven National Laboratory and at the Large Hadron Collider at CERN by smashing heavy atomic nuclei together at nearly the speed of light and creating, for a fraction of a second in the heart of the collision, a tiny droplet of quark-gluon plasma. Those experiments have told us something remarkable. The quark-gluon plasma does not behave like a gas of freely streaming particles, as physicists originally expected. It behaves like a liquid, a perfect liquid, in fact, one with the lowest viscosity, the lowest internal friction of any substance ever measured. It flows without resistance. It is the most frictionless fluid known to science. The early universe was filled, wall to wall, and as far as space extended, with this perfect, frictionless, burning soup of quarks and gluons and electrons and neutrinos and photons and every other elementary particle of the Standard Model, all of them present in roughly equal numbers, all of them in thermal equilibrium, all of them in a state of constant, frenetic, violent interaction. It was, in a very real sense, the most democratic moment in the history of the universe. Every particle present in equal abundance, every force in equilibrium. No structure, no hierarchy, no separation of any kind, just a roiling, perfect, primordial fire. In the quark-gluon plasma, something was happening that would determine whether the universe would ever contain anything at all. An asymmetry was developing, tiny in scale, enormous in consequence, between matter and antimatter. Every particle of matter has a corresponding antiparticle with the same mass, but opposite charge and other quantum numbers. The electron has the positron. The quark has the antiquark. When a particle and its antiparticle meet, they annihilate each other, converting their combined mass entirely into energy in the form of photons. In the early universe, matter and antimatter were being created and destroyed in equal amounts, constantly, in a thermal equilibrium. Pairs of quarks and antiquarks appeared from energy, existed briefly, and annihilated back into energy. Pairs of electrons and positrons flickered in and out of existence. The universe was a place of constant creation and destruction in perfect balance, or almost perfect balance. According to the physics of the Standard Model, and confirmed by experiment, the laws of physics are not perfectly symmetric between matter and antimatter. There is a slight, subtle difference in how certain particles behave compared to their antiparticles, a difference encoded in the mathematical structure of a weak force. This difference is called CP violation. CP violation means that in the quark-gluon plasma of the early universe, the rates of certain particle creation and annihilation processes were not exactly equal for matter and antimatter. Matter was created very slightly faster than antimatter, or antimatter annihilated very slightly faster, by an amount that is estimated to have been approximately 1 part in a billion. For every billion antiquarks, there were 1,000,000,001 quarks. For every billion anti-electrons, 1,000,000,001 electrons. When the universe cooled enough for quarks and antiquarks to annihilate for the last time, when the temperature dropped below the threshold for pair creation, the antimatter was almost entirely consumed. It met its matter counterpart and was annihilated in a final wave of photons. Almost all of the matter was annihilated too, but not quite all. That 1 in a billion excess of matter survived, and that tiny residue, that almost negligible asymmetry in the primordial plasma, is everything. It is every atom of hydrogen and helium that would go on to form the first stars. It is every carbon atom in every living thing that has ever existed on Earth. It is every planet, every moon, every galaxy, every structure in the observable universe. You exist because of a 1 in a billion imbalance in the particle physics of the first second. The universe very nearly created nothing but light. It very nearly annihilated itself before it could begin. The matter that survived was a rounding error in a cosmic calculation, and from that rounding error, everything was built. Let us pause for a moment and take stock of where the universe stands at the end of its first second of existence. 1 second old. The universe has expanded from the Planck scale to a volume roughly the size of our solar system. The temperature has dropped from 10 to the 32 degrees Kelvin to approximately 10 billion degrees Kelvin. 10 billion degrees is still an incomprehensible temperature, roughly 1,000 times hotter than the core of the sun. But it is a cooling universe. It is a universe on its way to becoming something. The 4 fundamental forces are now all distinct, all operating separately, each with its own character and range and strength. Gravity pulls matter together. Electromagnetism organizes charged particles. The strong force will soon begin binding quarks into protons and neutrons. The weak force will mediate certain transformations between particle types. The quark-gluon plasma is cooling toward the threshold at which quarks will combine permanently into hadrons, into protons and neutrons and other composite particles. This threshold will be crossed in the next fraction of a second, And when it is, the basic building blocks of atomic nuclei will exist for the first time. The matter-antimatter asymmetry has played out. The antimatter is gone, annihilated in a final blaze of radiation that adds its energy to the already luminous universe. The surviving matter, 1 part in a billion, is all that remains as substance. Everything else is radiation, a sea of photons carrying the energy of a billion annihilations. Neutrinos, ghostly particles that interact only through the weak force, have decoupled from the rest of the matter. They are now streaming freely through the universe, carrying information about the first second of its existence. A cosmic neutrino background, analogous to the cosmic microwave background, but consisting of neutrinos rather than photons, fills the universe. We have not yet directly detected it, because neutrinos interact so weakly with matter that detecting a background of them requires instruments we have not yet built. But it is there, right now, passing through you at this very moment. Every second, trillions of cosmic neutrinos from the Big Bang pass through every square centimeter of your body. You are bathed in the first second of the universe's existence, and you cannot feel it. The universe is 1 second old. It has already done more than any other second in the history of everything we'll ever do. I want to pause here at the end of the first second and do something slightly different. I want to try to describe not the physics, but the quality of this moment, the texture of it, as best as language can reach towards something that no language was designed to describe. The universe at 1 second old is not a place. It is not a location you could travel to or stand within. It is the totality of everything, the entire extent of space in all directions, and it is everywhere filled with the same thing. Light, not light as you experience it, the gentle photons of sunlight or the warm glow of a lamp. Energy, pure, undifferentiated, blazing electromagnetic radiation at a temperature of 10 billion degrees. A fire with no edge, no center, no outside. A fire that is everything, everywhere, simultaneously. And woven through this fire, in numbers almost too large to contemplate, the first particles. Electrons and their antiparticles, positrons still numerous and interacting. Neutrinos streaming freely, ghostly and uncoupled. And the quarks and gluons just beginning their final cooling toward combination, hovering on the threshold of becoming the first protons and neutrons. There is no silence in this universe. There is only the roar of 1 trillion interactions per particle per second. Every point in space is the site of an unimaginable number of collisions, annihilations, creations, and transformations. There is no stillness. There is no emptiness. There is no cold corner, no dark pocket, no region of rest. The universe is entirely, completely, perfectly alive with energy. And it is beautiful. This is something worth sitting with. The early universe, for all its violence, for all its incomprehensible heat and density and furious activity, was also extraordinarily beautiful. Not beautiful in the way a sunset is beautiful, or the way a piece of music is beautiful, because there was no one to see it or hear it, no consciousness to appreciate it, but beautiful in a mathematical sense, in the sense that the physicist means when they use that word. Symmetric, elegant, governed by simple, deep, powerful laws that produce this extraordinary complexity from almost nothing. The beauty of the early universe is the beauty of equation that works, the beauty of a pattern that holds at every scale, the beauty of something that could not have been otherwise, that was in some deep and not entirely understood sense necessary. You are made of that beauty. The same laws that governed the quark-gluon plasma at 1 second after the Big Bang govern the electrons and the neurons firing in your brain right now as you listen to these words. The same fundamental physics, the same deep symmetries. You are the universe at 1 second, grown older and cooler and more complex, but not less beautiful. Differently beautiful, beautifully different. In the next chapter, we will follow the universe through the remainder of its first few minutes. We will watch the quarks combine into protons and neutrons. We will witness the first nuclear reactions, the primordial nucleosynthesis that forged the first atomic nuclei, the hydrogen and helium and trace amounts of lithium that compose the oldest matter in the universe. We will watch the universe cool from 10 billion degrees toward 1 billion degrees, from a state of searing luminous plasma towards something slightly more structured, slightly more organized, still unimaginably hot by any ordinary measure, but beginning, just beginning, to be a place where things could persist. We will watch the first atoms fail to form and the universe fill with an opaque, glowing fog of unbound particles that will persist for hundreds of thousands of years before the next great transformation. But that is the next chapter. For now, we are at the end of the first second. The universe is 1 second old, 10 billion degrees, expanding and cooling and full of matter and light, and the first free quarks condensing toward the first protons. Let your mind rest here for a moment in the fire. Not the terrifying, destructive fire of something burning that should not be burning, but the primordial fire. The first fire. The fire that did not burn anything because there was nothing yet to burn, because it was everything, and everything was it. Let the warmth of that idea settle into you. You came from fire, not metaphorically, not poetically, though it is also that. Literally. The atoms of your body passed through fire at the beginning of time, in the quark-gluon plasma of the first second, before they were even atoms, before they were even protons. You were there, in your most fundamental constituents, in the deepest ancestral sense of the word, in the fire of the beginning. And here you are now, in the quiet and the dark, listening. That is quite a journey, and we have barely begun. There's a question that children ask, and that scientists have spent centuries trying to answer properly, because it turns out that answering it properly leads you straight to the heart of the universe. What is everything made of? Not the surface answer, not atoms, not molecules, not elements from a periodic table. The deep answer, the answer at the bottom of all the other answers, where you can go no further because there is nothing smaller, nothing simpler, nothing more fundamental beneath. The answer that physics has arrived at, after centuries of peeling back the layers of matter like the layers of an onion, so large it contains everything, is both simpler and stranger than most people expect. At the very deepest level that we currently understand, everything in the universe is made of two kinds of things. Fermions, the particles of matter, and bosons, the particles that carry forces between them. A small number of fermion types, 6 kinds of quarks, and 6 kinds of leptons, including the familiar electron, and a small number of boson types carrying the 4 fundamental forces. 12 matter particles, and a handful of force carriers. That is the complete inventory of the fundamental ingredients of everything. Every atom in your body, every star in every galaxy, every photon of light that has ever crossed the universe, every gravitational wave that has ever rippled through space-time. All of it, every last bit of it, composed of combinations and interactions of these few dozen fundamental fields. It is, by any measure, a remarkable economy. And in the quark epoch, the period from roughly 10 to the negative 12 seconds to approximately 10 to the negative 6 seconds after the Big Bang, the universe was doing the fundamental work of assembling these ingredients. It was the cosmic moment when matter began to organize itself into its most basic, recognizable pieces. Let us take a moment to understand what a quark actually is, because the word is used so often in popular science that it can begin to feel familiar without ever becoming truly understood, like a word in a foreign language that you recognize by sound without knowing its meaning. A quark is a fundamental particle. It has no known internal structure, no smaller parts, no components. As far as we can currently determine, it is not made of anything. It simply is. It has mass. It has electric charge. It has a property called color charge that governs how it interacts with a strong nuclear force. And it has spin, a quantum mechanical property that has no exact classical analog, but is loosely analogous to the rotation of a tiny top. There are 6 types of quarks, which physicists call flavors. The up quark and the down quark are the lightest and most stable, and they are the ones that compose all ordinary matter. The strange quark, the charm quark, the bottom quark, and the top quark are heavier and unstable, decaying rapidly into lighter quarks under ordinary conditions. They existed abundantly in the hot early universe, but have been vanishingly rare in the universe ever since, except when briefly created in high-energy collisions. The up quark has an electric charge of positive 2/3. The down quark has a charge of negative 1/3. 2 up quarks and 1 down quark, bound together by the strong force, form a proton, with a total charge of positive 1. 1 up quark and 2 down quarks form a neutron, with a total charge of 0. These 2 particles, the proton and the neutron, are the building blocks of atomic nuclei, and atomic nuclei combined with electrons are the building blocks of every atom. And every atom is the building block of everything you have ever seen or touched or been. Quarks cannot exist in isolation. This is one of the strangest properties of a strong force, the force that binds quarks together. The strong force does not weaken with distance the way gravity and electromagnetism do. It stays roughly constant as quarks are pulled apart like a rubber band rather than the loosening grip of a hand at a distance. Pull 2 quarks apart far enough, and the energy you put into the separation becomes large enough to create new quark-antiquark pairs from the vacuum itself, and the quarks snap back into bound states. You never end up with a free quark. The quarks are permanently, inescapably confined. This property is called confinement, and it means that quarks have spent essentially all of cosmic history locked inside composite particles. They have been inside protons and neutrons for 13.8 billion years, and they will remain inside them for a time so vast it makes the current age of the universe seem like a heartbeat. But in the quark epoch, they were free. The temperature was too high, the thermal energy too great for confinement to take hold. And in that freedom, in that extraordinary primordial liberty, they swarmed through the universe in their billions of billions, interacting and separating and interacting again in the quark-gluon plasma we described in the last chapter. Alongside the quarks in the primordial plasma, in numbers even greater than the quarks themselves, were the particles that carry the strong force. Their name was chosen with a pleasing and entirely literal simplicity. They're called gluons. A gluon is the force-carrying boson of the strong nuclear force. When 2 quarks interact via the strong force, they do so by exchanging gluons, the way 2 electrically charged particles interact by exchanging photons. But gluons have a property that photons do not. Gluons themselves carry color charge. This means that gluons interact with other gluons. The carriers of the strong force feel the strong force. This self-interaction is what gives the strong force its unusual character, its behavior that does not weaken with distance, its extraordinary strength at short ranges. In the quark-gluon plasma of the quark epoch, gluons were present in enormous numbers, constantly being exchanged between quarks, constantly interacting with each other, carrying energy and momentum and color charge through the blazing medium of the early universe. They were the invisible scaffolding of the primordial soup, the constant messengers of the force that would eventually bind everything together. And they were fast, because gluons, like photons, are massless. They travel at the speed of light. In the quark epoch, the strong force was being communicated across the universe at the maximum possible speed, instantly on any scale that mattered, weaving the quarks and gluons into a medium of staggering dynamism. At approximately 10 to the negative 6 seconds, 1 microsecond after the Big Bang, something changes. 1 microsecond, 1 millionth of a second, still almost too small to contemplate, and yet enormous compared to the timescales we have been discussing. In the time since the Big Bang, the universe has aged by a factor of 1,000,000 from the Planck time to this moment. It has cooled dramatically from the almost incomprehensible temperatures of the first instance to approximately 2 trillion degrees Kelvin. 2 trillion degrees is still unimaginably hot, far beyond anything achievable in any natural environment in the current universe outside of certain extreme astrophysical events. But it is cool enough for one crucial threshold to be crossed. The quarks begin to combine. As the temperature drops below approximately 2 trillion degrees, the strong force finally achieves what it has been waiting for. The thermal energy of the quark-gluon plasma drops below the level that prevents confinement, and quarks snap together into bound composite particles. This transition, from a plasma of free quarks and gluons to a gas of composite particles bound by the strong force, is called the QCD phase transition, where QCD stands for quantum chromodynamics, the theory of the strong force. The composite particles formed at this transition are called hadrons, from the Greek word for thick or heavy. The most familiar hadrons are the proton and the neutron, the building blocks of atomic nuclei. But in the hot conditions of the early universe, many other unstable hadron types were created as well. Pions, kaons, lambdas, sigmas, and dozens of other particles that exist today only briefly in high-energy collisions, but were abundant in the primordial hadron gas. The universe enters what is called the hadron epoch, and for a brief but eventful period, it is a universe composed primarily of hadrons, interacting and annihilating and being recreated in the thermal equilibrium of an extraordinarily hot and dense medium. Let's pause for a moment and appreciate the proton, because the proton is one of the great achievements of nature, a particle of such extraordinary stability, such perfect engineering, that it has endured essentially unchanged since the first microsecond of the universe, and will endure, barring processes we have never observed and whose existence is only theoretically speculated, for a time so vast it makes the current age of the universe look like an instant. A proton consists of 3 quarks, 2 up quarks and 1 down quark, bound together by a constant exchange of gluons. But here is the remarkable thing. The mass of those 3 quarks accounts for only about 1% of the proton's total mass. The remaining 99% comes from the energy of the gluons and the constant quantum mechanical motion of the quarks themselves, the kinetic and potential energy of a strong force field, converted into mass through Einstein's equation. You are, in the most literal sense, made almost entirely of the energy of the strong nuclear force. The mass of your body, the weight you feel on the scale, the inertia you feel when you start moving or stop, is almost entirely the energy of the color field, the gluon field, the strong force field inside your protons and neutrons. The quarks themselves contribute almost nothing to your mass. You're a creature of field energy dressed up in quarks. The proton is also, so far as we have ever been able to determine, absolutely stable. No one has ever observed a proton decay. The lower limit on the proton's lifetime, set by careful experiments involving enormous tanks of pure water deep underground, monitored for years for the faintest flash of light that might indicate a proton decay event, is approximately 10 to the 34th years. 10 to the 34th years. The universe is 13.8 billion years old, which is approximately 10 to the 10th years. The proton is stable for at least 10 to the 24th times longer than the current age of the universe. Some theories predict that protons do eventually decay on timescales of 10 to the 36th years or longer. If they do, the universe will eventually be a place with no atoms, no chemistry, no matter as we know it. But that is so far in the future that the word future barely applies. For all practical and many impractical purposes, the proton is eternal. And it was born in the quark-gluon plasma 1 microsecond after the Big Bang. As the hadrons form and the hadron epoch proceeds, another class of particles remains abundant and important. These are the leptons, and the most familiar of them is the electron. Electrons are fundamental particles, like quarks, in that they have no known internal structure. But unlike quarks, electrons do not feel the strong force. They interact only through electromagnetism and the weak force in gravity. They are therefore not confined. They move freely through space, interacting with photons and with each other and with the charged hadrons that now fill the universe. At the temperatures of the lepton epoch, which follows the hadron epoch, as the temperature drops below roughly 10 billion degrees Kelvin, electrons and their antiparticles, positrons, are still being created and annihilated in thermal equilibrium. For every electron, there's a positron. For every positron, there's an electron. The universe is full of them, colliding and annihilating into photons and being recreated from photons in a constant, rapid cycle. And then, as the temperature drops further, the pair creation of electron-positron pairs ceases. The thermal photons no longer have enough energy to create electron-positron pairs spontaneously. The equilibrium tips. The electrons and positrons annihilate for the last time. And once again, the matter-antimatter asymmetry asserts itself. The positrons are slightly fewer than the electrons. When the annihilation is complete, a small residue of electrons remains, exactly matching the number of protons that have already formed. The universe, after this final annihilation, has precisely as many electrons as protons, which is exactly what you need for electrical neutrality, for the formation of atoms, for the chemistry of a universe that will eventually produce stars and planets and living things. The universe, in a lepton epoch, found its electrical balance. It became, for the first time, a place where atoms could eventually exist. Not yet, not for hundreds of thousands of years, but the conditions were being prepared. Let us linger here for a moment, in the lepton epoch, in the universe's first few seconds, and simply admire what has happened. In less time than it takes to blink your eyes, the universe went from an undifferentiated quantum fluctuation, from a state we cannot even fully describe, to a place containing protons, neutrons, and electrons in precisely the right proportions for atoms and chemistry and complexity to eventually be possible. It went from nothing, or from something so close to nothing that the difference barely matters, to the basic architecture of all matter. The quarks assembled into protons and neutrons. The electrons survived their antimatter counterparts. The forces separated and found their individual characters. The laws of physics, operating at the extreme conditions of the first seconds, produced exactly the inventory of particles and forces needed for the next 13 billion years of cosmic history. There is something almost musical in this progression, like a symphony that begins with a single undifferentiated sound and slowly, movement by movement, separates into distinct voices, each one contributing its own character to the whole, each one constrained by the same underlying mathematical structure. The universe began as a single note and differentiated over its first seconds into the chord that is everything. You are one of the voices in that chord. A very late and locally complicated voice, it is true. A voice that took 13 billion years to develop from the first note. But the note is in you. The mathematics is in you. The quarks that assembled in the first microsecond are still there, locked in the protons and neutrons of every atom of your body, unchanged, eternal, patient. The universe built you from its very first pieces. And in the next chapter, we will watch it take the next great step. The forging of the first atomic nuclei, the first chemical elements, the first raw materials of stars and planets, and everything that will eventually follow. The first 3 minutes are coming, and they are extraordinary. There is a book written in 1977 by the physicist Steven Weinberg, one of the architects of the Standard Model of particle physics and a Nobel laureate, that carries one of the most quietly magnificent titles in the history of science writing. The first 3 minutes. 3 minutes. It sounds almost modest. 3 minutes is how long it takes to boil an egg. 3 minutes is the length of an average pop song. 3 minutes is the time you might spend standing at a window, watching rain fall against the glass, your thoughts drifting nowhere in particular, your body at rest, the world outside going about its ordinary business. And yet, in the first 3 minutes after the Big Bang, the universe accomplished something that has never been repeated and never will be. It created all of the hydrogen and almost all of the helium and a small, but precisely measurable amount of lithium that now exist in the observable universe. It forged, in the furnace of its own beginning, the raw material from which every star that has ever burned was built, and from which every atom of every element that makes chemistry and geology and biology possible was eventually assembled. The first 3 minutes are where the universe became a place that could eventually contain us. Let's go there together. We left the universe at the end of the lepton epoch, a few seconds after the Big Bang, with a temperature falling through tens of billions of degrees and a composition of protons, neutrons, electrons, neutrinos, and photons, the matter-antimatter annihilations largely complete, the residue of surviving matter now constituting the entire material content of the cosmos. At this point, the protons and neutrons exist freely, unbound, moving through the photon-rich plasma like individual dancers in a crowded room, occasionally colliding, occasionally exchanging particles, maintaining a thermal equilibrium between themselves. The ratio of neutrons to protons at this moment is determined by the temperature and by the physics of the weak force, which mediates the transformations between the two. At very high temperatures, neutrons and protons convert into each other rapidly and are present in roughly equal numbers. As the universe cools, however, the weak force interactions slow down. Neutrons and protons stop converting into each other as efficiently. And because the neutron is slightly heavier than the proton, slightly less energetically favorable, the ratio begins to tip. By the time the universe is about 1 second old, there are approximately 7 protons for every neutron. 7 to 1. Remember that ratio. It matters enormously for everything that follows. As the temperature falls through roughly 10 billion degrees, the universe crosses a threshold that physicists call neutrino decoupling. The neutrinos, which have been maintaining thermal equilibrium with the rest of the matter through the weak force, find that the universe has expanded and cooled to the point where their interactions become too rare to keep them in equilibrium. They decouple. They stream freely away from the rest of the matter, carrying their energy with them into the expanding cosmos, never to interact significantly with ordinary matter again. These relic neutrinos, the cosmic neutrino background, fill the universe to this day. They're everywhere around you right now, a sea of particle from the first second of time, passing through everything, interacting with essentially nothing. You are, at this very moment, immersed in the afterglow of the first second of the universe. You cannot feel it. Nothing can feel it in the ordinary sense of the word, but it is there. The universe continues to cool. The temperature drops through 1 billion degrees, and at this threshold, approximately 100 seconds after the Big Bang, something begins that will define the chemical composition of the cosmos forever. Nuclear fusion ignites for the first time. A temperature of 1 billion degrees Kelvin is the temperature at which atomic nuclei can begin to form and survive. Below this temperature, the thermal photons no longer have enough energy to immediately break apart any nucleus that forms. The strong force gets its first real opportunity to do what it does best: bind protons and neutrons together into stable configurations. This process is called Big Bang nucleosynthesis, and it is one of the most beautifully confirmed predictions in all of cosmology. The first nucleus to form is the simplest possible: deuterium. A deuterium nucleus consists of 1 proton and 1 neutron, bound together by the strong force. Deuterium had been forming briefly throughout the earlier hot phases of the universe, but every deuterium nucleus that formed was immediately blasted apart by the intense radiation of high-energy photons. This is called the deuterium bottleneck, the fact that nucleosynthesis could not proceed until the universe cooled enough for deuterium to survive. And at 100 seconds and 1 billion degrees, the bottleneck opens. Deuterium forms and survives. And with deuterium available, a cascade of nuclear reactions begins almost immediately. 2 deuterium nuclei can fuse to form helium-3, a nucleus with 2 protons and 1 neutron, releasing a neutron in the process. Or they can fuse to form tritium, a nucleus with 1 proton and 2 neutrons, releasing a proton. Helium-3 and tritium can then react with each other or with additional deuterium to form helium-4, the most stable light nucleus, with 2 protons and 2 neutrons. Small amounts of lithium-7 are also synthesized as helium. 4 nuclei capture additional neutrons and protons. All of this happens in a window of time that is astonishingly brief. Big Bang nucleosynthesis begins at roughly 100 seconds after the Big Bang and is essentially complete by approximately 17 minutes. In those 17 minutes, the universe produces essentially all of the helium, for it will ever contain roughly 25% of the total mass of ordinary matter in the cosmos. It produces the deuterium and helium-3 and lithium-7 in smaller but precisely predictable amounts. 17 minutes. The universe built the foundation of all chemistry in 17 minutes. Here, the 7-to-1 ratio of protons to neutrons becomes decisive. The neutron, as we noted, is slightly heavier than the proton. This means that a free neutron, one not bound inside a nucleus, is unstable. It decays through the weak force into a proton, an electron, and an antineutrino. The half-life of a free neutron is approximately 10 minutes and 11 seconds. This is one of the most precisely measured quantities in all of nuclear physics. Between the moment of neutrino decoupling, when the 7-to-1 ratio was established, and the moment of deuterium formation, when nucleosynthesis could finally begin, time passed. About 100 seconds of it. And during those 100 seconds, some of the free neutrons decayed. By the time nucleosynthesis began, the ratio had shifted slightly from 7 to 1 to approximately 6 to 1. Now, every neutron that is incorporated into a helium-4 nucleus is protected. Inside the nucleus, the strong force stabilizes it against decay. But every neutron that does not find a nuclear partner decays into a proton within minutes. By the time nucleosynthesis is complete, essentially all the surviving neutrons are locked safely inside helium-4 nuclei. The remaining protons, the vast majority of the matter, have no neutron partners and remain as bare protons, as bare hydrogen nuclei. The result, approximately 75% of the ordinary matter in the universe is hydrogen. Approximately 25% is helium-4. A tiny fraction is deuterium and helium-3 and lithium, and essentially nothing else. The rest of the periodic table, every element from carbon to uranium, does not yet exist in any significant quantity. It will be built later inside stars, over billions of years of stellar nucleosynthesis. But the hydrogen and helium of the first 3 minutes is still with us. Look up at the night sky. Every star you can see is burning primarily the hydrogen forged in the first 3 minutes after the Big Bang. The Sun, our own middle-aged star, is a ball of first 3 minutes hydrogen undergoing nuclear fusion in its core. The light that warms the Earth, the light that drove the photosynthesis that built every cell of every plant that has ever lived, is energy released by the burning of primordial hydrogen. You are in a very direct chain of causation, powered by the Big Bang. The predictions of Big Bang nucleosynthesis are not vague. They are precise. The theory does not merely predict that hydrogen and helium exist. It predicts the exact ratios of hydrogen to helium to deuterium to helium-3 to lithium-7 that should have been produced as a function of a single free parameter, the density of ordinary matter in the early universe. And astronomers can test these predictions. They can look at the oldest stars in the universe, stars that formed from gas clouds that had not yet been significantly enriched by stellar nucleosynthesis, stars whose chemical composition therefore reflects the primordial abundances. They can look at the spectra of ancient gas clouds in the intergalactic medium, absorbing the light of distant quasars, measuring the ratios of different atoms along the line of sight. And what they find matches the predictions of Big Bang nucleosynthesis with extraordinary precision. The helium fraction in the oldest objects in the universe is approximately 24 to 25%, consistent with the prediction. The primordial deuterium abundance, measured in ancient quasar absorption systems, matches the prediction. The lithium abundance is slightly more complicated, the so-called cosmological lithium problem, where observed lithium in old stars seems to be somewhat lower than predicted. But this discrepancy is small and may reflect processes occurring within the stars themselves rather than errors in the nucleosynthesis model. This agreement between prediction and observation, across multiple independent measurements using multiple different techniques, is one of the pillars of modern cosmology. It tells us that we genuinely understand the physics of the first 3 minutes, that the equations we are using, the standard model of particle physics applied to the conditions of the early universe, are correct, that the Big Bang model is not a story we have invented, but a description of something that actually happened. The universe left a receipt, and we can read it. After the first 3 minutes, after nucleosynthesis is complete, the universe enters a long, relatively quiet phase. Quiet by comparison, at least to the extraordinary violence of what has just occurred. The universe is now composed primarily of hydrogen nuclei and helium nuclei, along with electrons and photons and the freely streaming neutrinos we mentioned earlier. The temperature is still hundreds of millions of degrees, still far too hot for electrons to bind to nuclei and form neutral atoms. Every time an electron approaches a nucleus and the two begin to form an atom, a high-energy photon comes along and blasts them apart again. The universe is opaque. Photons cannot travel more than a tiny distance before they are absorbed and re-emitted by free electrons in the plasma. Imagine the universe at this stage as an extraordinarily hot, dense fog, a luminous mist in which light cannot travel freely, in which every photon is constantly scattered and redirected by the sea of charged particles through which it moves. There is light everywhere. The universe is blazing with radiation, but it is a blind universe in the sense that this radiation carries no information about structure or form, because the universe has no structure or form yet. It is uniform. It is smooth. It is, apart from the tiny quantum fluctuations planted by inflation, featureless. This state will persist for a very long time. For 380,000 years, the universe will remain in this condition. Hot, dense, opaque, a glowing plasma of hydrogen and helium nuclei and free electrons, bathed in radiation, expanding slowly, cooling gradually, waiting for the temperature to drop to the threshold at which atoms can finally form. 380,000 years is a long time. It is roughly 28 times the entire span of recorded human history. It is a patient waiting, a slow cooling, an almost imperceptible approach to the moment of transformation. But the transformation, when it finally comes, will be one of the most important events in the history of the universe. It will be the moment the universe becomes transparent, the moment light is set free, the moment the first structure begins to form, the moment the long dark road towards stars and galaxies and planets and life truly begins. We will reach that moment soon. In Chapter 5, we will sit with the universe in its long, glowing wait. We will feel the slow passage of those 380,000 years, and we will arrive at the threshold together. But for now, rest here. Rest in the afterglow of the first 3 minutes. Let the idea of primordial nucleosynthesis settle slowly into you, the way the hydrogen and helium settled slowly out of the cooling plasma into the structures that would become stars. The recipe for the universe was written in the first 3 minutes, and it has been cooking slowly and magnificently ever since. There is something I want to offer you before we move on, a thought that I find quietly overwhelming every time I sit with it long enough to really feel it. The hydrogen in the water you drank today, the hydrogen bonded to oxygen in every molecule of H2O in your body, that hydrogen has existed in essentially its current form since the first 3 minutes of the universe. For 13.8 billion years, those protons have been protons. They were forged in the quark-gluon plasma of the first microsecond. They survived the matter-antimatter annihilation. They were present during Big Bang nucleosynthesis, most of them remaining as bare protons, as hydrogen nuclei, while a quarter of their companions bonded with neutrons to become helium. They drifted through the dark ages of the universe. They fell into the first gas clouds. They were gathered into the first stars and, in many cases, were not fused but passed through, emerging again into the interstellar medium when the star died. They drifted again. They were gathered into later generations of stars, into the nebula that formed our solar system, into the ocean of the early Earth, into the first living cells, through billions of years of biological evolution, through the food chain, through rain and rivers and groundwater and agriculture and digestion, and into you. That proton in the water you drank today has been on a journey of 13.8 billion years to reach your lips. You are not separate from the Big Bang. You are not a visitor to a universe that existed before you arrived. You are the Big Bang, in one of its most recent and local and improbable configurations. You are what the first 3 minutes eventually became, given time and gravity and chemistry and the patient, relentless creativity of a universe that cannot stop making things. That is a true thing, a physical, measurable, scientifically confirmed true thing. Hold it gently as you drift towards sleep. The universe made you from its very first moments, and it is not finished yet. There is something I want to offer you before we move on, a thought that I find quietly overwhelming every time I sit with it long enough to really feel it. The hydrogen in the water you drank today, the hydrogen bonded to oxygen in every molecule of H2O in your body, that hydrogen has existed in essentially its current form since the first 3 minutes of the universe. For 13.8 billion years, those protons have been protons. They were forged in the quark-gluon plasma of the first microsecond. They survived the matter-antimatter annihilation. They were present during Big Bang nucleosynthesis, most of them remaining as bare protons, as hydrogen nuclei, while a quarter of their companions bonded with neutrons to become helium. They drifted through the dark ages of the universe. They fell into the first gas clouds. They were gathered into the first stars, and in many cases were not fused but passed through, emerging again into the interstellar medium when the star died. They drifted again. They were gathered into later generations of stars, into the nebula that formed our solar system, into the ocean of the early Earth, into the first living cells, through billions of years of biological evolution, through the food chain, through rain and rivers and groundwater and agriculture and digestion, and into you. That proton in the water you drank today has been on a journey of 13.8 billion years to reach your lips. You are not separate from the Big Bang. You are not a visitor to a universe that existed before you arrived. You are the Big Bang, in one of its most recent and local and improbable configurations. You are what the first 3 minutes eventually became, given time and gravity and chemistry and the patient, relentless creativity of a universe that cannot stop making things. That is a true thing, a physical, measurable, scientifically confirmed true thing. Hold it gently as you drift towards sleep. The universe made you from its very first moments, and it is not finished yet. To understand why these 380,000 years matter so much, and why their ending was such a transformative event, you need to understand what the universe was like during this period. What would have felt like if feeling had been possible to exist within it. Imagine standing inside a star. Not near a star, not orbiting a star, but inside one. Inside the core of a star like our sun, where the temperature is 15 million degrees and the density is roughly 150 times that of water, and the pressure is so extreme that a column of material the width of your thumb running from the core to the surface would weigh more than all the world's oceans combined. Inside a star, you cannot see. Not because there is no light, there is an abundance of light. The core of the sun is blazing with the energy of nuclear fusion, but because the light cannot travel. Every photon produced in the core is immediately absorbed by the surrounding plasma, re-emitted in a random direction, absorbed again, re-emitted again, in a random walk that takes the energy and average of 100,000 years to travel from the core to the surface, where it is finally released and begins the 8-minute journey to Earth. The universe during the first 380,000 years was like the inside of a star, but in every direction, everywhere, without end. A universe-sized stellar interior. Hot, dense, opaque, blazing with trapped radiation that could not travel freely in any direction. In such a universe, the concept of seeing makes no sense. There are no vistas. There are no horizons. There are no distant objects to observe because light cannot travel far enough to carry information about distant objects. The universe is not dark during this period. It is the opposite of dark. It is blindingly, universally bright with trapped radiation. But it is a brightness without information, without structure, without image. It is light that tells you nothing except that it is there. And everything is the same. Look in any direction and you see the same glowing plasma. Move to any location and you find the same temperature, the same density, the same composition. The universe during the plasma era is the most homogeneous large-scale environment that has ever existed. It is the same everywhere to a precision of about 1 part in 100,000. 100,000. That is the magnitude of the variations from place to place. Tiny fluctuations in density that were seeded by quantum randomness during inflation and that will eventually, given time and gravity, grow into every structure we observe in the cosmos. But for now, they are invisible against the overwhelming uniformity. The universe is waiting, and it is, in a very deep sense, alone with itself. But I told you the waiting was not idle. And here is one of the most beautiful and least known stories in cosmology, a story about what the plasma era actually contained beneath its apparent uniformity. The plasma of the early universe was not truly static. The tiny density variations seeded by inflation, those 1 in 100,000 fluctuations in the density of matter and radiation, were the source of pressure differences in the plasma. A region that was slightly denser than average had slightly higher pressure. That higher pressure pushed outward, compressing the surrounding plasma. The compression raised the pressure of the neighboring region, which pushed back, and so on. The early universe was full of sound waves. Not sound in the sense of what you hear with your ears, which requires air pressure waves vibrating at frequencies your eardrums can detect, but pressure waves in the plasma, traveling outward from every density perturbation, reflecting and interfering and propagating through the luminous medium of the early universe at a speed determined by the physics of the photon-baryon fluid. These pressure waves moved at approximately half the speed of light. They are called baryon acoustic oscillations, and they left a mark on the universe that we can still detect today, 13 billion years later, in the distribution of galaxies across the sky. The characteristic scale of these ancient sound waves, the distance they had traveled by the time the plasma era ended, is imprinted in the statistical clustering of galaxies at a particular separation, a bump in what astronomers call the power spectrum of the galaxy distribution. This bump has been measured, and its scale matches the predictions of the Big Bang model with extraordinary precision. We can hear the echo of the sound waves of the early universe in the arrangement of galaxies across the sky. The universe's most ancient music, played in a medium that no longer exists, is still audible if you know how to listen. The plasma was not quiet. It was singing. It was full of pressure waves and oscillations and the constant restless motion of particles in thermal equilibrium. All of it building toward the moment when the singing would stop, the plasma would clear, and the music would be frozen into the large-scale structure of the cosmos forever. While the plasma sang and the photons ricocheted and the universe expanded and cooled with patient inevitability, something else was happening. Something slower, quieter, and ultimately more consequential for the long-term future of the cosmos. Gravity was taking notes. The density fluctuations seeded by inflation, those tiny 1 in 100,000 variations in the distribution of matter across space, were already being noticed by gravity. Regions that were slightly denser than average had slightly more gravitational attraction than their surroundings. They were pulling matter in from the regions around them, very slowly, very gradually, almost imperceptibly, but consistently, relentlessly, with the patient certainty of a force that never stops operating and never gives up. During the plasma era, this gravitational growth was inhibited. The photons and the baryons, the ordinary matter, were tightly coupled to each other. The radiation pressure of the photons resisted the compression of the baryons into denser clumps. Gravity pulled in, radiation pushed back. The result was the oscillations we just described, the baryon acoustic oscillations, the universe's plasma-era sound waves. But there was another component of the universe that gravity could work on without opposition. A component that did not interact with photons, did not feel radiation pressure, did not participate in the plasma oscillations. A component that could simply fall quietly and without resistance into whatever gravitational wells the density fluctuations created. This component is dark matter. We will discuss dark matter in detail in a later chapter. For now, it is enough to say that dark matter, which makes up approximately 27% of the total energy content of the universe, compared to about 5% for ordinary visible matter, was already forming structures during the plasma era. While the ordinary matter oscillated and the photons scattered and the universe appeared smooth and uniform, the dark matter was quietly, invisibly assembling itself into the first cosmic scaffolding, the first gravitational skeleton that would eventually guide ordinary matter into the filaments and nodes of the cosmic web. The visible universe was waiting. The invisible universe was already at work. 380,000 years. Let us try together to hold that span of time in mind, not to fully comprehend it, because no human mind can truly comprehend it, but to gesture toward it, to feel its scale. Modern Homo sapiens have existed for approximately 300,000 years. The entire span of our species, from the first anatomically modern humans in Africa to the civilization that built the telescopes and particle accelerators that discovered the Big Bang, is shorter than the plasma era of the early universe. If you compress the plasma era into a single day, the entire history of our species would occupy approximately 18 hours of it. And the entirety of recorded human history, the 10,000 years from the first cities to the present, would be less than 4 minutes. And yet in cosmic terms, the plasma era is brief. It represents less than 0.003% of the age of the universe. It is a rounding error in the account of cosmic time. But within it, the universe was doing its slow work, expanding, cooling, dropping from the hundreds of millions of degrees of the post-nucleosynthesis era toward the threshold that would change everything. That threshold is approximately 3,000 degrees Kelvin. 3,000 degrees sound hot, and is hot by ordinary standards. It is roughly the temperature of the surface of a moderately cool star, hotter than anything you will ever directly encounter in daily life. But compared to the temperatures of the early universe, it is remarkably, almost paradoxically cool. 3,000 degrees is the temperature at which electrons and nuclei can finally stay together. The temperature at which thermal photons no longer have enough energy to blast apart the electrostatic bond between a negatively charged electron and a positively charged nucleus. The temperature at which atoms, for the first time in the history of the universe, become possible. And at 380,000 years after the Big Bang, the universe reached that temperature. The event is called recombination. The name is slightly misleading because the electrons and nuclei were not combining for a second time. They had never combined before. This was the first time. But the name has stuck, borrowed from the language of plasma physics, and it refers to the moment when electrons and atomic nuclei combine to form neutral atoms throughout the universe. Imagine it happening, not at a single instant, but over a period of perhaps tens of thousands of years, a gradual transition as the temperature fell through the 3,000-degree threshold. In the denser regions first, where the local conditions crossed the threshold slightly earlier, electrons began to bind to hydrogen and helium nuclei and stay bound. The photons that had been constantly scattering off these electrons suddenly found their path cleared. With fewer free electrons in the way, the photons could travel further before scattering, and further, until, in a transition that, from a cosmological perspective, was remarkably swift, the universe became transparent. Think about what this means. For 380,000 years, no photon had traveled more than a tiny distance before being absorbed and re-emitted. The universe had been completely, uniformly opaque. Every point in space was surrounded by an impenetrable fog of scattering electrons. And then, over a cosmologically brief period, that fog lifted. The electrons locked into atoms. The photons, freed from their constant scattering, streamed outward in straight lines. For the first time in the history of the universe, light could travel. For the first time, there was a distinction between here and there, between this direction and that one, between near and far. For the first time, if there had been eyes to see, there would have been something to see. The universe, at the moment of recombination, became a place. Not a smooth, featureless plasma in which all locations were interchangeable. A place with regions that were slightly denser and regions that were slightly less dense, with the tiny but real variations in temperature and matter distribution that would, under the long patient influence of gravity, eventually become everything. When the universe became transparent at recombination, the photons that were released at that moment began their journey through the cosmos. They have been traveling ever since, through the expanding universe, through the dark ages, through the epoch of reionization, through the formation of galaxies and galaxy clusters and the cosmic web, for 13.4 billion years, cooling and redshifting as space expanded around them. Those photons are still traveling today, and they're arriving at Earth right now. At this very moment, as you lie in the dark listening to these words, photons that were released at the moment of recombination, the moment the universe first became transparent, are striking the antennas of radio telescopes and the detectors of space-based observatories all over the planet. They are arriving from every direction in the sky, with almost perfect uniformity, carrying the imprint of the universe at the moment they were last scattered, the moment they were set free. This radiation is the cosmic microwave background, the CMB, the single most important piece of observational evidence in modern cosmology, the fossil light of the Big Bang. We will explore it in great depth in the next chapter. For now, simply hold this image. The photons released at recombination define what cosmologists call the last scattering surface, a spherical shell centered on our location in space, 380,000 light-years in radius as measured in the early universe, now stretched by the expansion of space to a distance of approximately 46 billion light-years, a surface from which we receive the oldest light in the universe. Beyond that surface, in the earlier, opaque plasma, we cannot see. The last scattering surface is the literal edge of the observable universe, the wall of time beyond which electromagnetic radiation cannot carry information to us. Everything we can see with light, every galaxy, every quasar, every nebula, every star lies between us and this wall. And the wall itself glows faintly and uniformly in the microwave frequencies with the afterglow of the Big Bang. We live inside a sphere of ancient light. The universe's oldest photograph, taken at 380,000 years of age, surrounds us in every direction, 30 billion light years away, in every direction simultaneously. It is, if you allow yourself to really feel it, one of the most astonishing facts in the history of human knowledge. And what did the universe look like at the moment of recombination, at the moment it first became transparent? It looked like fog, dense, warm, glowing fog. Not the cool gray fog of a winter morning, but a luminous reddish-orange fog, the color of the light emitted by gas at 3,000 degrees, similar to the color of a dim red star. In every direction, the universe glowed with this warm, uniform light. The sky, if there had been a sky to speak of rather than simply a universe in every direction, would have been a featureless, smoothly glowing orange-red. There were no stars, no galaxies, no planets, no structures of any kind visible to any instrument we can imagine. Just the vast, smooth, gently glowing gas, hydrogen and helium atoms newly formed, expanding through the cooling universe, carrying within their distribution the tiny, barely perceptible density variations that gravity would soon begin to amplify. It was beautiful in the way that vast, empty things can be beautiful, the way the open ocean is beautiful, or the way a clear sky before sunrise is beautiful, before the first birds call and before the colors begin to change. A beauty of scale and simplicity and potential. A beauty that comes from being at the beginning of something enormous. Because that is what this moment was. The beginning of the next phase of cosmic history. The end of the plasma era and the beginning of what cosmologists call the Dark Ages. The long period before the first stars formed and filled the universe with new light. The fog had lifted. The universe was clear, and it was about to go dark, not because anything was wrong, not because the clearing was a setback, but because the light released at recombination would quickly redshift to invisibility as the universe expanded, and there were not yet any new sources of light to replace it. The stars had not yet formed. The galaxies had not yet assembled. The universe, freshly transparent, was about to enter its longest, quietest, darkest interval. 380,000 years of plasma. 380,000 years of waiting, of singing, of slow, invisible work. And now, a darkness deeper than any that had come before. The universe was clear and empty and patient, and somewhere in the smooth distribution of hydrogen and helium atoms drifting through the cooling dark, gravity was already finding its first footholds, pulling, concentrating, building the invisible scaffolding that would, over hundreds of millions of years, become the first stars. But that is for the next chapter. For now, let the clearing settle over you like the lifting of a fog you did not know was there. Let the universe be transparent for a moment. Let the ancient light travel. You are held inside it, even now. The oldest light in the universe is all around you in every direction, arriving at the speed of light from every point on the horizon of time. You are bathed in the Big Bang. Rest in that. There is a sound that has no source you can point to. A sound that does not come from any particular direction, but from every direction simultaneously, equally, without preference or variation, as though the air itself were vibrating at a frequency just below the threshold of hearing. You have felt something like it perhaps, standing inside a large empty building, a cathedral or concert hall, after the music has stopped, when the echo still hangs in the air, when the stone walls are still ringing with what was played, when the silence is not quite silent, because it is full of the memory of sound. The cosmic microwave background is something like that. It is the echo of the Big Bang, still ringing, still traveling, still arriving at this very moment from every direction in the sky, from every point on the horizon of the observable universe, carrying the imprint of the universe's earliest structured moment, the moment of recombination 380,000 years after the beginning. It is the oldest light in the universe. the furthest thing we can see, the wall at the edge of time, glowing faintly in the microwave frequencies, a whisper from an era before there were stars, before there were galaxies, before there was anything in the universe except hydrogen and helium atoms and the radiation they had just released into a newly transparent cosmos. And we have mapped it with extraordinary precision, with a detail and resolution that would have seemed like science fiction to the astronomers of even 50 years ago. We have mapped the cosmic microwave background across the entire sky and read from it, like text on an ancient document, the story of the universe's infancy. This chapter is about that map, about what it tells us, about the extraordinary human and scientific story of its discovery and measurement, and about what it means to hold, in the palm of your hand, metaphorically speaking, a photograph of the universe at 380,000 years of age. The cosmic microwave background was not found by someone who was looking for it. It was found by two radio engineers at Bell Telephone Laboratories in Homedale, New Jersey, who were trying to do something far more mundane and who were, for a considerable period of time, deeply frustrated by what they found. The year was 1964. Arno Penzias and Robert Wilson were working with a large horn-shaped radio antenna that Bell Labs had built for communication satellite experiments. The antenna was sensitive, precisely calibrated, and technically sophisticated for its era. Penzias and Wilson were attempting to use it for radio astronomy, mapping the faint radio emissions from the Milky Way. And they were running into a problem. There was noise in the system, a persistent, low-level hiss of microwave radiation that appeared in the data no matter which direction they pointed the antenna. It was uniform. It was constant. It did not vary with the time of day or the season or the direction of observation. It was not coming from the Milky Way. It was not coming from any identifiable cosmic source. It was simply there, everywhere, always, a faint and inexplicable background of microwave radiation that their instrument could not account for. They checked everything. They tested the electronics, recalibrated the detectors, examined every component of the system for sources of spurious noise. They found a pair of pigeons nesting inside the antenna horn and evicted them, cleaning out what they described with characteristic scientific understatement as a white dielectric material, pigeon droppings that had accumulated on the interior surfaces. They reassembled the antenna, pointed it at the sky, and measured again. The noise was still there. Frustrated and puzzled, Penzias and Wilson eventually contacted colleagues at Princeton University, where a group led by Robert Dick had actually been constructing an instrument specifically to search for the relic radiation from the Big Bang, motivated by theoretical predictions suggesting it should exist. The Princeton group had been anticipated. They heard about Penzias and Wilson's mysterious noise and immediately recognized it for what it was. Penzias and Wilson had accidentally discovered the cosmic microwave background, the most important astronomical observation of the 20th century, the observational cornerstone of modern cosmology, the echo of the Big Bang. They received the Nobel Prize in Physics in 1978. The pigeons, whose droppings had briefly complicated the most consequential radio astronomy observation in history, were not similarly honored. But they occupy a permanent, if undignified, footnote in the story of how humanity discovered the afterglow of its own origins. Let us be precise about what the cosmic microwave background actually is, because the phrase echo of the Big Bang, while evocative and not wrong, can create a slightly misleading impression if taken too literally. The CMB is not a reflection, is not a wave bouncing back to us from some distant surface. It is the original light itself, the photons released at recombination, still traveling, still arriving after 13.4 billion years of journey through the expanding universe. At the moment of recombination, 380,000 years after the Big Bang. The universe was at a temperature of approximately 3,000 degrees Kelvin and was filled with glowing plasma. When the electrons combined with nuclei and the universe became transparent, the photons that had been trapped in the plasma were released. They began to travel freely through the cosmos in every direction. Those photons had a temperature of 3,000 degrees. They were in the infrared and visible part of the electromagnetic spectrum, the warm orange-red light of a glowing gas at that temperature. They were in the wavelengths of light, perfectly ordinary thermal radiation, the kind of radiation emitted by any hot object. But the universe has been expanding ever since. And as the universe expands, the wavelengths of the photons traveling through it are stretched. The expansion of space itself stretches the electromagnetic waves, shifting them toward longer, lower energy wavelengths. This is the cosmological redshift and has been working on the CMB photons for 13.4 billion years. The result is that light, which was emitted at 3,000 degrees in the infrared and visible spectrum, has been stretched by a factor of roughly 1,000. Its wavelengths are now in the microwave range, the same range of electromagnetic radiation used by microwave ovens and some radar systems. Its equivalent temperature is no longer 3,000 degrees, but approximately 2.725 degrees above absolute zero, barely warmer than the coldest possible temperature. The most chilled down, most redshifted, most ancient light in the universe. The CMB photons are ancient. They have been traveling for longer than any other light in the observable universe. They carry information about a time before the first stars formed, before the first atoms had existed for more than a few tens of thousands of years. They are messengers from an era so remote and so different from the present that almost nothing about the universe they describe would be recognizable to us if we could somehow visit it. And they are everywhere. Right now, the room you are in is full of them. Every square centimeter of space around you is being crossed by approximately 400 CMB photons per second. They pass through the walls, through your body, through everything, with almost no interaction, because at microwave frequencies and at the density of the present universe, ordinary matter is very nearly transparent to them. You are, at this very moment, immersed in the oldest light in the universe. It is passing through you as you breathe, as your heart beats, as your thoughts form and dissolve in the quiet dark. The most remarkable thing about the cosmic microwave background is not its existence, extraordinary as that is. The most remarkable thing is its texture, its variation, its pattern. To a first approximation, the CMB is perfectly uniform. Every direction in the sky has the same temperature to a precision of about 1 part in 100,000. The universe at recombination was extraordinarily smooth and homogeneous. This smoothness is itself deeply significant and is one of the observations that inflation was designed to explain, because without inflation, there is no obvious reason why the universe should be so uniform in all directions. But to a second approximation, at the level of that 1 in 100,000 precision, the CMB is not perfectly uniform. There are tiny temperature fluctuations, tiny hot spots and cold spots scattered across the sky, regions where the plasma at recombination was very slightly denser or slightly less dense, slightly hotter or slightly cooler than average. These fluctuations are not random noise. They are not instrumental artifacts. They are a physical signal imprinted on the CMB by the acoustic oscillations of the early universe plasma, the baryon acoustic oscillations we discussed in the previous chapter, by the density perturbations seeded by inflation, and by various physical processes occurring during and after recombination. The pattern of temperature fluctuations across the sky is a complex but precisely predictable consequence of the physics of the early universe. And that pattern has been measured, first roughly by the COBE satellite in 1992, which made the first detection of the CMB temperature fluctuations and won its principal scientist the Nobel Prize in Physics in 2006. Then with greater precision by the WMAP satellite, which operated from 2001 to 2010 and produced detailed maps of the CMB across the full sky. And then with extraordinary, almost unbelievable precision by the Planck satellite, which observed from 2009 to 2013 and produced the most detailed map of the early universe ever made. The Planck map of the CMB shows the entire sky covered in a pattern of subtly varying temperature, a modeled landscape of blue and red and yellow indicating regions of the early universe that were very slightly cooler or very slightly warmer or very slightly denser than average. It looks at first glance like a blurry photograph of something you cannot quite identify, but is not blurry. It is a precise, information-rich map of the universe at 380,000 years of age, containing within its pattern the answers to some of the most fundamental questions in cosmology. The temperature fluctuations in the CMB are not just a pretty picture. They are a dataset of extraordinary richness, and cosmologists have spent decades developing the mathematical tools to extract from them every possible piece of information about the early universe and its subsequent evolution. The primary tool for analyzing the CMB fluctuations is the power spectrum, a mathematical decomposition of the temperature pattern across the sky into its constituent angular scales, telling you how much variation exists at each scale, from fluctuations spanning large regions of the sky to fluctuations at tiny angular scales. The power spectrum of the CMB has a characteristic shape with several peaks, called acoustic peaks, each one corresponding to a particular angular scale that reflects the physics of the baryon acoustic oscillations in the early universe plasma. The positions and heights of these acoustic peaks are extraordinarily sensitive to the fundamental parameters of the universe: the total energy density, the fraction of that energy in ordinary matter, the fraction in dark matter, the fraction in dark energy, the geometry of space itself, whether the universe is flat or curved, the spectrum of density fluctuations seeded by inflation, the optical depth to reionization, a measure of how much the CMB was rescattered after recombination. By fitting the observed CMB power spectrum to the predictions of the cosmological model, scientists can determine all of these parameters simultaneously, with precision that in some cases reaches fractions of a percent. The Planck satellite results, published in a series of papers beginning in 2013 and refined in subsequent analyses, determined that the universe is composed of approximately 5% ordinary matter, approximately 27% dark matter, and approximately 68% dark energy. That the universe is geometrically flat to extraordinary precision. That the age of the universe is 13.8 billion years, with an uncertainty of less than 1%. That the Hubble constant, the current rate of expansion of the universe, is approximately 67 kilometers per second per megaparsec, though this particular measurement has become the subject of a significant ongoing tension with other measurement methods that we will discuss later. All of this information, extracted from the subtle temperature variations of a faint microwave glow covering the entire sky, from photons that have been traveling for 13.4 billion years, from the light released when the universe was 380,000 years old. It is, without exaggeration, one of the most extraordinary achievements in the history of human knowledge. Science, when it is working well, does not only confirm what we expect, it also reveals what we did not expect. and the cosmic microwave background for all the extraordinary confirmation it provides for the standard cosmological model, also contains a few anomalies, a few features that do not quite fit the predictions, features that cosmologists are still working to understand. The most discussed of these is a feature sometimes called the cold spot. In the southern celestial hemisphere, in the direction of the constellation Eridanus, there's a region of the CMB that is slightly colder than average and larger than any cold region that the standard model of inflation would predict with high probability. It is not impossible within the standard model. It could be a statistical fluctuation, one of those rare but not inconceivable events that happen occasionally even in a universe governed by well-understood physics. But it is unusual enough to have attracted considerable attention and to have inspired a variety of proposed explanations, from a supervoid, a region of space unusually empty of matter, to more exotic suggestions involving topology or even the influence of neighboring universes in a multiverse. There is also a feature sometimes called the axis of evil, a somewhat dramatic name given to an apparent alignment of the largest scale features of the CMB temperature pattern with the plane of our solar system. This alignment is surprising because there is no obvious physical reason why features imprinted on the CMB at recombination should know anything about the orientation of our local solar system. If real, it could indicate some form of contamination of the CMB data by foreground emission from our own galaxy, or it could indicate something more profound about the large-scale structure of the universe. And then there is the Hubble tension. The value of the Hubble constant, the current rate of expansion of the universe, measured from the CMB using the Planck data, is approximately 67 kilometers per second per megaparsec. But the value measured by other, completely independent methods, using the cosmic distance ladder, the chain of distance measurements using Cepheid variable stars and type I supernovae, is approximately 73 kilometers per second per megaparsec. These two values disagree by an amount that is now statistically significant at more than 5 sigma, which in physics means the discrepancy is unlikely to be a chance fluctuation. Something is not adding up. Either one or both sets of measurements have systematic errors that have not yet been identified, or the standard cosmological model is incomplete, missing some ingredient that would reconcile the two values. This tension is currently one of the most actively debated problems in cosmology, and its resolution, whenever it comes, may require modifications to the standard model that will reshape our understanding of the universe. The CMB, the most precisely mapped object in astronomy, is not only a confirmation. It is also a question that the universe is asking physics in the form of a slight, persistent, stubbornly significant discrepancy in numbers. Science is healthiest when it has questions it cannot yet answer. Beyond the temperature fluctuations, the cosmic microwave background carries another layer of information, encoded not in the brightness of the light, but in its polarization, the direction in which the electric field of the electromagnetic wave oscillates. When photons scatter off electrons, they become polarized. The pattern of polarization in the scattered light carries information about the geometry of the scattering event, about the distribution of matter around the scattering electron, about the large-scale structure of the gravitational field at the moment of last scattering. And so the polarization pattern of the CMB, mapped across the sky, contains additional information about the early universe that is not present in the temperature map alone. The polarization of the CMB has been mapped with increasing precision by WMAP, by Planck, and by several ground-based experiments, including the BICEP telescopes at the South Pole. The measured polarization patterns are consistent with the standard cosmological model and have provided additional constraints on its parameters. One particularly exciting target for CMB polarization measurements is a specific pattern called B-mode polarization, which would be generated by primordial gravitational waves, the gravitational waves produced during inflation. If inflation occurred, it should have produced a background of gravitational waves that left a distinctive imprint on the CMB polarization. Detecting this signature would be the most direct confirmation of inflation ever achieved, a window into the physics of the very first fraction of a second of the universe's existence. In 2014, the BICEP 2 telescope announced what seemed to be the detection of this signature. The announcement was greeted with enormous excitement, but subsequent analysis revealed that the signal had been contaminated by polarized emission from dust in our own galaxy, and the primordial signal was not confirmed. The search continues. New, more sensitive instruments are being built and deployed. The primordial B-mode signal, if it exists at the level predicted by the most popular inflationary models, is within reach of the next generation of CMB experiments. The CMB has not yet given us everything it has to give. Let me offer you an image to carry with you as this chapter ends, and as you settle more deeply into the quiet dark of wherever you are. Imagine that you could take a photograph of the entire universe at a single moment in time. Not of a galaxy, not of a region of space, but of everything. All of space, in all directions, at one instant. And imagine that you could take that photograph when the universe was 380,000 years old, at the moment of recombination, at the moment it first became transparent, at the moment it released its first light into a newly clear cosmos. The photograph exists. It is not hypothetical. It is real. It has been taken by instruments built and launched and operated by thousands of scientists over decades of work by the COBE and WMAP and Planck satellites. The photograph is the CMB map, the oval projection of the entire sky, modeled with the barely perceptible temperature fluctuations of the infant universe, is the photograph of everything at the beginning. And when you look at it, when you study that pattern of blue and red and yellow across the sky, you're looking at the direct ancestor of every structure in the universe. The slightly blue, slightly cooler, slightly less dense regions in the CMB map are the precursors of the vast cosmic voids, the enormous empty spaces between galaxy filaments, the regions of the universe that contain almost nothing. The slightly red, slightly warmer, slightly denser regions are the precursors of the cosmic filaments, the walls and threads of dark matter and gas that contain most of the universe's mass, that host the galaxy clusters and groups and individual galaxies strung along their length like beads on a thread. The pattern in the CMB map is the universe's blueprint, the architect's drawing, the plan laid down at 380,000 years, from which everything else was eventually constructed. You are in that photograph. Not you personally, not your atom specifically, but your galaxy, your corner of the cosmic web, the large-scale structure that eventually gravity would assemble from the seeds visible in the CMB, all of that is already present in embryonic form in those tiny temperature fluctuations. The blueprint of your address in the universe was written when the universe was 380,000 years old and has been slowly, patiently, magnificently realized over the 13 billion years since. Look at the CMB map, and you're looking at your own distant origins, at the most ancient ancestor of your place in the cosmos. That is not poetry. That is physics. And it is worth a quiet moment of something like wonder before sleep comes. There is a particular kind of darkness that is different from all the other kinds. There is the darkness of a room with the curtains drawn, where you know that outside the window the world continues, lit by street lamps and stars and the faint ambient glow of a city that never entirely sleeps. There is the darkness of a forest at midnight, where your eyes adjust slowly and the shapes of trees begin to emerge from the shadows, where the darkness is populated, inhabited, alive with the sounds of unseen creatures. There is the darkness of the bottom of a deep ocean trench, crushing and cold, and yet full of its own strange bioluminescent life, creatures that have adapted over millions of years to thrive in the absence of sunlight. None of these is the darkness of the cosmic dark ages. The cosmic dark ages were not merely an absence of light in a place that had other things to offer. They were an absence of sources, an absence of fire, an absence of any process anywhere in the universe that was producing new photons in the visible spectrum. The CMB photons that have been released at recombination were still present, filling the universe with their fading, redshifting microwave glow, cooling further with every passing million years, receding deeper into the invisible spectrum. But in the wavelengths that matter to eyes and to the chemistry of life, invisible light and ultraviolet and the energetic photons that drive the processes we associate with warmth and activity, the universe was dark. Completely, perfectly, cosmically dark. This darkness lasted, depending on how precisely you define its beginning and end, for somewhere between 100 and 400 million years. A darkness measured not in hours or days or centuries, but in hundreds of millions of years. A darkness so deep and so total and so long that the word darkness, a word invented by creatures who experience it only in brief intervals punctuated by dawn, barely begins to capture its magnitude. And yet, in this darkness, the most important structural work in the history of the universe was being quietly, invisibly, patiently completed. Let us close our eyes, those of us whose eyes are still open, and try to inhabit the dark ages universe. Try to imagine being somewhere, anywhere, in the cosmos at, say, 50 million years after the Big Bang. You're surrounded by gas, an almost unimaginably thin gas by the standards of anything we encounter on Earth, thinner than the best vacuum we can produce in any laboratory, but present nonetheless, a diffuse medium of hydrogen and helium atoms drifting through expanding space. The temperature of this gas has dropped from the 3,000 degrees of recombination to perhaps a few hundred degrees. Still warm, but cooling steadily with every passing million years as the universe expands and the residual heat of the Big Bang dissipates into the growing volume of space. There is no light source anywhere near you. The CMB fills the universe, but at microwave frequencies that no eye could detect, that would register as nothing more than an imperceptible warmth if you could somehow feel electromagnetic radiation the way you feel sunlight on your skin. Invisible light. In the wavelengths that matter for seeing, the universe is dark. Absolutely, perfectly, uniformly dark. There is no structure near you, no galaxy, no star, no planet, no dust cloud that might eventually become any of these things. The gas around you is smooth, almost featureless, drifting and cooling, and on the very largest scales, not quite uniform. There are regions very slightly denser than average, regions where the seeds planted by inflation and amplified slightly by the acoustic oscillations of the plasma era have left their mark. But you would not see these variations. You would not feel them. There are differences of a fraction of a percent in the local density of a gas, already so thin it barely exists. The universe at 50 million years is not dramatic. It is not filled with fire or violence or the spectacular events that characterized its first seconds. It is quiet. It is dark. It is cold. It is the opposite of everything we tend to imagine when we think about the early universe, that blazing, furious beginning. And yet, gravity is working. Gravity is always working. And in those barely perceptible density variations, gravity has found its footholds, and it is pulling, and the pulling, though invisible and slow, is relentless. The structure of a universe that we observe today, the vast network of galaxy filaments and clusters and voids that astronomers call the cosmic web, was not built in a moment. It was not assembled quickly or dramatically or with any of the urgency that characterized the early universe's first seconds. It was built slowly, over hundreds of millions and then billions of years, by the patient, ceaseless, inexorable work of gravity acting on the dark matter and ordinary matter of the post-recombination universe. Dark matter, as we noted in an earlier chapter, does not interact with electromagnetic radiation. It does not emit light. It does not absorb light. It moves through the universe as if ordinary matter barely exists, responding only to gravity. And during the Dark Ages, this property made dark matter the universe's first and most efficient builder. While ordinary hydrogen and helium gas was still hot enough to resist gravitational compression, supported by its thermal pressure against the inward pull of gravity, the dark matter had no such thermal resistance. It could fall freely into any gravitational well, attracted by any density enhancement, accumulating in structures that did not need to overcome any pressure to form. And so the dark matter began to assemble itself during the Dark Ages into structures. The tiny density fluctuations in the dark matter distribution, imprinted by inflation and present since the very beginning, began to grow under gravitational attraction. Denser regions pulled in more material from their surroundings. The more material they accumulated, the stronger their gravitational pull. The stronger their pull, the more material they accumulated. A runaway process, slow at first, then accelerating, building over hundreds of millions of years from nearly imperceptible fluctuations into the massive dark matter halos, the invisible gravitational cocoons, inside which the first galaxies and stars would eventually form. Imagine it as a vast, three-dimensional web being woven in complete darkness. Threads of dark matter connecting nodes of dark matter. Vast sheets and filaments of invisible material assembling themselves across millions of light years. The scaffold of the cosmic web taking shape in the dark long before any light existed to illuminate it. Like a building whose steel skeleton rises in the night, invisible to any observer, but present and growing and defining the shape of what will eventually be seen when the lights are finally turned on. The cosmic web was being built in darkness, and when the first stars finally ignited and the darkness ended, the web was already there, already shaped, already defining the large-scale structure that the light would eventually trace. The Dark Ages are dark, but they're not entirely inaccessible to us. There's a way to see into them, a method that does not require visible light, that uses instead a very specific wavelength of radio emission produced by neutral hydrogen atoms under the conditions that prevailed during the Dark Ages. Neutral hydrogen atoms, the most abundant form of matter in the Dark Ages universe, can exist in two slightly different energy states, depending on the relative orientation of the spins of the electron and the proton that make up the atom. When a hydrogen atom transitions from the slightly higher energy state, in which the electron and proton spins are aligned in the same direction, to the slightly lower energy state, in which they are aligned in opposite directions, it emits a photon with a wavelength of exactly 21 centimeters and a frequency of approximately 1.42 gigahertz. This is the 21 centimeter line, one of the most important spectral features in radio astronomy. During the Dark Ages, the universe was full of neutral hydrogen, and this hydrogen was emitting and absorbing 21 centimeter radiation. The pattern of this emission and absorption, varying from place to place, and from time to time, as the distribution of hydrogen changed, and as the first sources of ionizing radiation began to appear, contains a detailed record of the large-scale structure of the universe during the Dark Ages and the subsequent epoch of reionization. Mapping the 21-centimeter emission from the Dark Ages is one of the most ambitious goals of current and near-future radio astronomy. It requires extremely sensitive radio telescopes capable of detecting faint signals from enormous redshifts, signals that have been stretched by the expansion of the universe from their original 21-centimeter wavelength to wavelengths of several meters or more. Instruments like the Square Kilometre Array, currently under construction in South Africa and Australia, are being built partly with this goal in mind. We have not yet mapped the Dark Ages in 21-centimeter radiation with anything like the detail we would like. But the first hints of this signal have been detected, and the prospect of eventually producing a full three-dimensional map of the Dark Ages universe, a map showing the large-scale structure of the hydrogen distribution across hundreds of millions of years of cosmic history, is one of the most exciting prospects in observational cosmology. The Dark Ages were dark to visible light, but they were not silent, and we're learning, slowly, to listen, while the dark matter assembled its invisible scaffold and the neutral hydrogen drifted and cooled through the expanding universe. The ordinary matter of the Dark Ages was doing its own slow, patient preparation for what was to come. The hydrogen and helium atoms of the post-recombination universe were not in their final, stable, ground state configurations immediately after recombination. Many of them have been formed in excited states, their electrons occupying higher energy levels than the ground state, and they were slowly cascading down through the energy levels, emitting photons as they did so. This slow relaxation added a faint glow to the early post-recombination universe, a glow that faded over tens of thousands of years as the atoms settled into their lowest energy configurations. By a few million years after the Big Bang, essentially all of the hydrogen and helium was in its ground state, neutral and stable, and the universe was truly dark. No more recombination radiation, no more cascading electrons, just the cold, neutral gas expanding through the dark, and the fading microwave background receding deeper into the invisible spectrum with every passing million years. The temperature of the gas continued to fall. 100 degrees Kelvin, 50, 20, 10. The gas was cooling toward the temperature at which, in the densest regions, it would eventually be able to collapse under gravity against its own thermal pressure and form the first stars. That temperature, determined by the physics of the hydrogen molecule, is a few hundred degrees Kelvin, still cold by terrestrial standards, but warm enough that the newly formed molecular hydrogen could radiate away its energy and allow gravitational collapse to proceed. But the gas had to first form molecular hydrogen, a process that requires either dust grains as catalysts, which do not yet exist in the pristine primordial gas, or the presence of trace amounts of hydrogen anions, hydrogen atoms with an extra electron, which can form in very small quantities and serve as the seeds for molecular hydrogen formation. This is a slow process, and it meant that the Dark Ages universe had to wait, cooling and drifting for the conditions to become right for the very first stellar ignitions. The universe was patient. It had already waited 380,000 years for atoms to form. It could wait another few hundred million years for stars. I want to pause here in the middle of the cosmic Dark Ages and offer you something that is not strictly scientific, but that I think is essential to truly feeling, rather than merely knowing, the story we are telling tonight. The cosmic Dark Ages lasted, at minimum, somewhere between 100 and 400 million years. Let's take 200 million years as a reasonable estimate of their duration. 200 million years of total, unbroken, universal darkness. No stars, No galaxies, no fire of any kind, just cold, dark, expanding gas and the invisible scaffold of dark matter growing in the silent dark. 200 million years ago from today, the dinosaurs were in the middle of the Triassic period. The continents were still mostly joined in the supercontinent Pangaea. The first dinosaurs were small, bipedal creatures that had only recently evolved from their archosaur ancestors. The Atlantic Ocean did not exist. The Rocky Mountains had not yet formed, and modern humans were still approximately 200 million years in the future. That is 200 million years measured forward from a known reference point, a period so vast that it encompasses the entire history of the dinosaurs, the breakup of Pangaea, the formation of the modern ocean basins, the rise and fall of dozens of geological eras, the evolution from early archosaurs to every form of life alive on Earth today. The cosmic dark ages were as long as all of that, and during all of that equivalent time, the universe contained nothing that produced light, nothing that warmed a surface or cast a shadow or reflected in any water. Just the dark gas and the dark matter and the patient work of gravity, assembling in silence the architecture from which everything bright and warm and structured would eventually be built. It is a scale of darkness almost impossible to genuinely feel. And yet, in a strange way, it is also quietly beautiful. There is a beauty to patience, a beauty to the long preparation before a great event, a beauty to the darkness before the dawn, understood not as deprivation but as gestation, as the necessary quiet before the extraordinary eruption of light that was coming. The universe was not failing during the Dark Ages. It was preparing. It was doing, in darkness, the slow and necessary work without which the light would have been impossible. You, lying in whatever darkness surrounds you now, are perhaps doing something similar. In sleep, in the quiet, in the darkness, the mind does its own preparation, consolidates, repairs, reorganizes. The darkness of sleep is not an absence of life, but a different mode of it, one that makes the waking hours possible, that gives them their structure and their meaning. The universe rested in darkness for 200 million years, and what followed was extraordinary. By somewhere between 100 and 300 million years after the Big Bang, the conditions in the densest regions of the dark matter halos had reached the threshold for gravitational collapse of ordinary matter. The dark matter halos had grown massive enough to create deep gravitational wells. The ordinary gas, hydrogen, and helium had been slowly falling into these wells throughout the Dark Ages, accumulating in the centers of the dark matter structures. The gas had been cooling as it fell, radiating away its thermal energy through the emission of photons, allowing gravity to compress it further. And in the densest, most concentrated regions, the gas was reaching the conditions required for the first nuclear reactions to ignite. The temperature at the center of a contracting gas cloud was rising. Hundreds of degrees, thousands, tens of thousands, hundreds of thousands. The density was increasing. The pressure was building. The protons at the center were being pushed closer and closer together by the weight of the gas above them. And then, in the first object to cross the threshold, at a moment that we cannot date precisely, but that occurred somewhere in the range of 1 to 400 million years after the Big Bang, the temperature at the center reached 10 million degrees. The protons were close enough together that the strong nuclear force could reach across the gap between them. Two protons collided and fused. A deuterium nucleus was born. Another fusion reaction followed, and another. The first star ignited. After hundreds of millions of years of darkness, the universe made fire, and nothing would ever be the same. We will watch that fire in all its extraordinary and alien glory in the next chapter. We will meet the first stars, the population 3 stars, the most massive and most brilliant and shortest-lived stars the universe has ever produced, the stellar pioneers that burned bright and died fast, and in dying, seeded the cosmos with the first heavy elements. But for now, rest here at the threshold, at the edge of the darkness and the dawn. Feel the weight of the 200 million years of silence that preceded this moment. Feel the patience of the gas and the dark matter, the long, slow preparation, the gestation of the cosmos. The universe waited 200 million years to make its first star. The wait was worth it. Think about what it means to be first. Not first in a race, where others have run the same course before, and the track is marked, and the distance is known, and the rules are established, and the only question is who crosses the line ahead of whom. Think about being first in the deeper sense. The first creature to walk on land, pulling itself out of the sea into an environment that nothing had ever inhabited before. The first human to stand at the edge of an ice sheet that no member of our species had ever crossed and decide to cross it anyway. The first mind to look up at the night sky and ask not merely what those points of light were, but how they came to be there. Being first means doing something without the guidance of precedent, without the comfort of knowing that others have done it and survived, without the accumulated wisdom of generations who came before and learned from their mistakes. Being first means writing the first line of a story that did not exist before in a language that had to be invented to write it. The first stars were first in the most absolute sense that the word can carry. There had never been stars before. Not one. Not anywhere in the universe. The cosmos had existed for somewhere between 100 and 400 million years and had contained, in all of that time and across all of the vast, expanding volume of space, nothing that burned by nuclear fusion, nothing that converted matter into energy in the sustained, self-regulating way that defines a star. The universe had been dark and cold and quiet and structureless in the stellar sense. For an interval so long it makes all of recorded human history look like a single frame of a very long film. And then, in the darkness, a point of light appeared, and then another, and the dark ages ended. Astronomers classify stars into populations based on their chemical composition, specifically on the abundance of elements heavier than hydrogen and helium. These heavier elements, everything from carbon and oxygen to iron and gold and uranium, are called metals by astronomers, a usage that has nothing to do with the everyday meaning of the word. A metal, in astronomical language, is simply any element heavier than helium, regardless of its chemical properties. The stars we see in the night sky today, including our own sun, are population 1 stars. They are relatively rich in metals, having formed from gas clouds that had already been enriched by many generations of previous stars that lived, fused heavy elements in their cores, and scattered those elements into the interstellar medium when they died. Our sun is approximately 2% metals by mass, which sounds like a small fraction, but represents an enormous enrichment over the primordial composition of the universe. Older stars, found primarily in the ancient globular clusters that orbit the Milky Way like satellites, are population 2 stars. They formed earlier from gas that had been less thoroughly enriched by previous stellar generations, and they are poorer in metals, sometimes by factors of 10,000 or more compared to the sun. But the very first stars, the ones that formed from the pristine primordial gas of the Dark Ages, the gas that came directly from Big Bang nucleosynthesis with essentially no heavy elements at all, those are population 3 stars. And they were unlike any stars that have ever existed since. The primordial gas was, to a very good approximation, pure hydrogen and helium. No carbon, no oxygen, no nitrogen, no iron, no silicon, no dust grains, nothing that the subsequent generations of stars would take for granted as part of their formation environment. Just the two simplest atoms, in a ratio established by Big Bang nucleosynthesis, drifting through the dark in the gravitational wells assembled by dark matter during the Dark Ages. This purity had profound consequences for the stars that formed from it. The absence of heavy elements in the primordial gas meant that the gas cloud from which the first stars formed could not cool as efficiently as later gas clouds can. Modern star-forming gas clouds contain carbon monoxide, water molecules, and other molecular species that are extraordinarily efficient at radiating away thermal energy, allowing the gas to cool to very low temperatures before collapsing into stars. Cold gas can collapse into small, dense fragments, producing the relatively modest stars, like our Sun, that characterize modern star formation. The primordial gas had no such cooling agents. It could cool only through the emission of radiation from molecular hydrogen, a much less efficient process. This meant the gas clouds of the Dark Ages remained warmer as they collapsed. Warmer gas has higher pressure. Higher pressure resists fragmentation. And so instead of breaking up into many small stars the way modern molecular clouds do, the primordial gas clouds tended to collapse into a smaller number of much larger, more massive objects. The theoretical models of population 3 star formation, developed over decades of increasingly sophisticated computer simulations, suggest that the first stars were extraordinarily massive by modern standards. While typical stars forming today range from a fraction of a solar mass to perhaps a few tens of solar masses, population 3 stars are thought to have ranged from perhaps 30 to several hundred solar masses, with some models suggesting that the very first stars may have been even more extreme, approaching or exceeding 1,000 solar masses. 1,000 solar masses. Imagine a star containing the mass of 1,000 suns, compressed into a single blazing object. Such a star would be so luminous, so incandescently brilliant, that it would outshine our entire present-day Milky Way galaxy by itself. It would burn so hot that its surface temperature would be perhaps 100,000 degrees Kelvin, 5 times hotter than the surface of the sun, pouring out ultraviolet radiation and X-rays in quantities that would ionize the hydrogen gas for enormous distances around it. Its radiation pressure, the pressure of the light it emitted, would be so intense that it would approach the theoretical limit at which the radiation pressure itself prevents additional mass from falling onto the star. These are the most extreme stars the universe has ever produced. Objects of a scale and luminosity and violence that have not existed anywhere in the observable universe for more than 13 billion years, and that will never exist again, because the pristine, uncontaminated primordial gas from which they formed has been gone since the first generation burned through it and enriched it forever with the products of their nuclear furnaces. The first stars were unique, singular. They were, in the most literal sense, the universe's first draft of the concept of a star, written in conditions that will never be repeated, in a language of pure hydrogen and helium that no subsequent star has ever spoken. A star's lifespan is determined, in large part, by its mass, and a relationship is counterintuitive. The more massive a star, the shorter its life. Not because massive stars have less fuel, they have enormously more fuel than small stars, but because the nuclear fusion in their cores proceeds at such a ferocious rate, driven by the extreme pressure of so much overlying mass, that they burn through their fuel at a proportionally far greater pace. Our Sun, with its 1 solar mass, will spend roughly 10 billion years on the main sequence, steadily fusing hydrogen in its core. A star of 10 solar masses burns through its fuel in perhaps 30 million years. A star of 100 solar masses lives for only about 3 million years. A star of 500 solar masses if such a thing existed, and the theoretical models suggest it did in the early universe, might live for only 1 or 2 million years. 1 or 2 million years. Our species, Homo sapiens, has existed for approximately 300,000 years. A 500 solar mass population 3-star would have lived and died, completing its entire stellar existence before our ancestors had even appeared on Earth. And yet, in that brief, blazing existence, such a star would have accomplished something of enormous cosmic importance. It would have fused in its core quantities of heavier elements, helium from hydrogen, carbon and oxygen from helium, neon and magnesium from carbon, silicon and sulfur from oxygen, and finally iron, the end of the stellar fusion chain, in quantities proportional to its enormous size. It would have been a cosmic chemistry laboratory, building the periodic table from scratch, adding to the universe's inventory of heavy elements that had not existed since the Big Bang. And then it would have died. The deaths of the first stars were among the most violent events the universe has ever produced. And they were, in a very real sense, the most important deaths in cosmic history. Because it was in those deaths that the first heavy elements were scattered into the universe, that the primordial purity of the gas was ended forever, and that the enrichment of the cosmos that would eventually lead to planets and chemistry and life truly began. When a massive star exhausts the nuclear fuel in its core, the core collapses under gravity in a fraction of a second. The collapse generates a shock wave that blasts the outer layers of the star into space at a significant fraction of the speed of light. This is a core collapse supernova, and it is one of the most energetic events the present-day universe produces. For a few weeks, a single supernova can outshine an entire galaxy of hundreds of billions of stars. But the supernovae of the first stars were potentially even more spectacular. The most massive population 3 stars, those exceeding perhaps 140 solar masses, are believed to have died in a different and even more violent way. Apparent stability supernova. In the cores of the most massive stars, at the extreme temperatures reached near the end of their lives, a process occurs in which the intense gamma-ray radiation in the core produces pairs of electrons and positrons directly from the radiation energy. This pair production absorbs energy from the radiation field, reducing the radiation pressure that has been helping support the star against gravity. The core begins to contract. The contraction raises the temperature further, accelerating the pair production, reducing the pressure further, driving a catastrophic collapse that triggers an explosive nuclear burning event so energetic that it completely destroys the star. There is no remnant, no neutron star, no black hole. Nothing is left. The entire star, every solar mass of it, is converted into energy and heavy elements and blasted into the surrounding universe at velocities approaching 1/10 of the speed of light. Apparent stability supernova releases roughly 100 times the energy of an ordinary core collapse supernova. It is the universe's most complete form of stellar self-destruction. And from these titanic explosions, the first heavy elements were flung across the cosmos. Carbon, oxygen, silicon, calcium, iron, elements that had not existed in any significant quantity since the universe began. Elements that would mix with the surrounding primordial gas, enriching it, changing its cooling properties, enabling the formation of the next generation of stars, and eventually, over billions of years of stellar evolution, making possible the formation of rocky planets and the chemistry of life. The first stars died so that everything else could eventually live. The deaths of the first stars were not the only dramatic effect of their brief, blazing existences. Their lives, while they lasted, transformed the universe around them in another equally profound way. The first stars, blazing at temperatures of 50,000 to 100,000 degrees, poured out ultraviolet radiation in quantities that dwarfed anything the modern universe produces. This ultraviolet radiation was energetic enough to ionize hydrogen atoms, to strip the electrons from the protons and return the hydrogen to the plasma state it had been in before recombination. And this process, called reionization, transformed the state of the intergalactic medium, the diffuse gas filling the space between galaxies, from neutral to ionized. Reionization did not happen all at once. It happened in patches spreading out from each newly formed star or group of stars like bubbles growing in a pot of water just beginning to boil. The first stars ionized the gas immediately around them, creating growing spheres of ionized hydrogen called HI regions or Strömgren spheres, named after the Danish astronomer Bengt Strömgren, who first calculated their properties. As more and more stars formed, these bubbles of ionized gas grew and spread and eventually overlapped, percolating through the neutral intergalactic medium until, by approximately 1 billion years after the Big Bang, the process was essentially complete. The universe, which had been filled with neutral hydrogen since recombination, was once again filled with a plasma of free protons and electrons. The intergalactic medium had been reionized, and it has remained ionized ever since, maintained in that state by the ultraviolet radiation of the billions of galaxies that have formed and evolved over the subsequent 12 billion years. Reionization marks the end of the cosmic dark ages in the most complete sense. Not only had the first stars ended the darkness by providing new sources of visible light, they had fundamentally changed the chemical state of the universe's gaseous content, creating the ionized intergalactic medium that modern astronomers observe when they study the absorption spectra of distant quasars. The universe, in the era of reionization, became something recognizable, something that, if you squinted past the enormous distances and timescales, bore a structural resemblance to the universe we observe today, a web of matter and radiation and ionized gas, lit by fires organized by gravity, beginning the long process of assembling the structures we call galaxies. Here is a remarkable fact. In all of the history of astronomy, across all of the observations made with all of the telescopes and instruments ever built, not one confirmed population 3 star has ever been directly observed. Not one. They're the most important stars in the history of the universe. They ended the Dark Ages. They produced the first heavy elements. They triggered reionization, and we have never seen one. The reason is not difficult to understand. Population 3 stars were extremely massive and therefore extremely short-lived. They formed in the first few hundred million years of the universe and died within a few million years of their formation. By the time the universe was 1 billion years old, the first generation of truly pristine, metal-free massive stars was gone. And the distances involved in observing objects from that era are so enormous, the light so thoroughly redshifted, that detecting individual stars from that epoch has been beyond the capabilities of every telescope we have built. But this is changing. The James Webb Space Telescope, launched in December 2021 and operating since mid-2022, is specifically designed to observe the earliest structures in the universe, to peer back to the epoch of the first stars and galaxies with a sensitivity and resolution that no previous instrument has approached. Its infrared detectors are tuned to the wavelengths at which the light from the first billion years of the universe arrives at Earth, redshifted from ultraviolet and visible into the infrared by 13 billion years of cosmic expansion. Webb has already revealed galaxies forming at extraordinarily early times. Galaxies existing less than 300 million years after the Big Bang. galaxies whose brightness and structure have surprised even the astronomers who designed the telescope and who had expected to find the earliest structures to be smaller and dimmer than what they observed. The early universe was forming stars and galaxies more rapidly and more vigorously than the Standard Model predicted, a discrepancy that cosmologists are actively working to understand. And some of the light reaching web from the most distant, most ancient galaxies may contain, woven into the spectrum of the galaxy's collective light, the signatures of population 3 stars, helium emission lines, the absence of certain metal absorption features, the fingerprints of stellar population made of almost pure hydrogen and helium. We may be on the verge of the first indirect detection of the first stars. The first stars have been waiting in their light for us to build an instrument capable of receiving their message. 13 billion years of travel, from the epoch of reionization to the infrared detectors of a telescope orbiting the Sun at a gravitationally stable point 1.5 million kilometers from Earth. And perhaps, at last, we will read what they wrote in the spectrum of their light. Let us close this chapter with something personal, with an accounting of what the first stars gave us. Not in the abstract, cosmic sense, but specifically materially in terms of what is sitting in the room with you right now. The oxygen you're breathing. Every atom of it was forged inside a star. Not necessarily a population 3 star. Oxygen is produced more efficiently in slightly lower mass stars. But the chain of stellar nucleosynthesis that produced the oxygen in your lungs began with population 3 stars, which enriched the gas for which the subsequent generations of stars formed. The carbon in your body. Every carbon atom in every molecule of DNA in every cell of your body was forged inside a star, in the triple alpha process by which 3 helium nuclei fused to form a carbon nucleus at temperatures of hundreds of millions of degrees in stellar cores. That process began in the universe, inside the cores of the first stars. The calcium in your bones, the iron in your blood, the silicon in the electronics of whatever device might be playing this audio, the gold and silver and copper in any jewelry or coins you might own. All of it, without exception, forged in stars. All of it descended through generations of stellar births and deaths and supernovae and gas clouds and new star formation from the original act of nucleosynthesis that began with the population 3 stars of the Dark Ages. You are made of the deaths of the first stars, not metaphorically, not poetically, though it is also that. Every heavy atom in your body passed through at least one stellar core before it became part of you. Some of your atoms have passed through multiple generations of stars, recycled through supernovae and gas clouds and new star formation over billions of years, before finding their way into the solar nebula that became our sun and planets, into the ocean of the early Earth, into the chemistry of life, into the food chain, into you. You're the first stars, grown old and cool and complex and conscious, sitting in the dark wondering where you came from. Now you know. There's a word that astronomers use when they want to describe a galaxy, a word that sounds almost too simple for something so vast and so ancient and so structurally magnificent, but that captures something essential about what a galaxy is in relation to everything around it. They call an island of stars in an ocean of darkness, a bounded, self-contained collection of matter, held together by its own gravity, surrounded by the almost empty intergalactic medium, separated from the nearest neighboring island by distances so enormous that the stars within the island, for all their numbers, for all the hundreds of billions of them burning and dying and orbiting within the gravitational embrace of the whole, amount to a density almost negligibly small compared to the volume of space the galaxy occupies. A galaxy is mostly empty space, almost entirely empty space. The stars within it are separated from each other by distances measured in light years, each one isolated in its own vast bubble of vacuum, interacting with its neighbors only through gravity and the faint passage of light across years and decades and centuries of emptiness. If you shrank the sun to the size of a grain of sand and placed it on a table, the nearest star would be another grain of sand approximately 25 kilometers away on the other side of the city, with nothing between them but vacuum. And yet, seen from a sufficient distance, a galaxy glows. The collective light of those hundreds of billions of widely separated stars adds up to something visible, something beautiful, something that a sufficiently sensitive telescope can detect from distances of billions of light years. The islands shine, and the ocean between them is dark. Tonight we watch the first islands form. We watch the darkness begin to organize itself, under the patient guidance of gravity, into the structures that will define the large-scale architecture of the universe for the rest of cosmic time. A galaxy does not appear all at once. It does not blink into existence at a single moment. It assembles slowly and through a complex interplay of processes from the raw material provided by the cosmic gas and the dark matter scaffolding that has been building since the Dark Ages. The process begins with the dark matter halos we discussed in earlier chapters. During the Dark Ages, dark matter assembled itself into clumps and filaments and sheets under its own gravitational attraction, building the invisible cosmic web that would eventually guide the distribution of ordinary matter across the universe. The largest, most massive dark matter concentrations, the nodes of the cosmic web where multiple filaments intersect, provided the deepest gravitational wells, the places where ordinary matter, gas falling in from all directions along the dark matter filaments, would accumulate most rapidly and most densely. As ordinary gas fell into these dark matter halos, it was compressed and heated by the gravitational energy of its infall. A gas cloud falling into a deep gravitational well converts its gravitational potential energy into kinetic energy, and then, through collisions between atoms, into heat. The infalling gas arrived hot, at temperatures of millions of degrees, forming a hot diffuse atmosphere within the dark matter halo called the hot halo gas, or the circumgalactic medium. This hot gas then had to cool in order to form stars. And cooling for a diffuse gas in a dark matter halo is a slow process, dependent on the density and composition of the gas and on the efficiency of the radiative cooling processes available. In the regions where cooling was most efficient, where the gas was densest, and where trace amounts of metal from the first stellar generation had already enriched it slightly, the gas cooled and sank toward the center of the halo, forming a dense, cold disk of gas rotating around the center of the dark matter concentration. In this disk, the gas density eventually reached the threshold for star formation, and stars began to form, in clusters and associations, illuminating the disk from within with their collective light. A proto-galaxy had been born. The first galaxies were small by modern standards. Dwarf galaxies, containing perhaps a few million to a few hundred million stars, a tiny fraction of the hundreds of billions that populate a mature spiral galaxy, like the Milky Way. They were irregular in shape, clumpy, active with star formation, blazing with the light of young hot stars being born from the enriched gas left behind by the first stellar generation. They were nothing like the stately, symmetric spirals and ellipticals that dominate the modern universe. They were the rough drafts, the first prototypes, the initial experiments in a process of assembly that would continue for billions of years. A galaxy does not appear all at once. It does not blink into existence at a single moment. It assembles slowly and through a complex interplay of processes from the raw material provided by the cosmic gas and the dark matter scaffolding that has been building since the Dark Ages. The process begins with the dark matter halos we discussed in earlier chapters. During the Dark Ages, dark matter assembled itself into clumps and filaments and sheets under its own gravitational attraction, building the invisible cosmic web that would eventually guide the distribution of ordinary matter across the universe. The largest, most massive dark matter concentrations, the nodes of the cosmic web, where multiple filaments intersect, provided the deepest gravitational wells, the places where ordinary matter, gas falling in from all directions along the dark matter filaments, would accumulate most rapidly and most densely. As ordinary gas fell into these dark matter halos, it was compressed and heated by the gravitational energy of its infall. A gas cloud falling into a deep gravitational well converts its gravitational potential energy into kinetic energy, and then, through collisions between atoms, into heat. The infalling gas arrived hot, at temperatures of millions of degrees, forming a hot diffuse atmosphere within the dark matter halo called the hot halo gas, or the circumgalactic medium. This hot gas then had to cool in order to form stars. And cooling for a diffuse gas in a dark matter halo is a slow process, dependent on the density and composition of the gas and on the efficiency of the radiative cooling processes available. In the regions where cooling was most efficient, where the gas was densest, and where trace amounts of metals from the first stellar generation had already enriched it slightly, the gas cooled and sank toward the center of the halo, forming a dense, cold disk of gas rotating around the center of the dark matter concentration. In this disk, the gas density eventually reached the threshold for star formation, and stars began to form in clusters and associations, illuminating the disk from within with their collective light. A proto-galaxy had been born. The first galaxies were small by modern standards. Dwarf galaxies containing perhaps a few million to a few hundred million stars, a tiny fraction of the hundreds of billions that populate a mature spiral galaxy like the Milky Way. They were irregular in shape, clumpy, active with star formation, blazing with the light of young hot stars being born from the enriched gas left behind by the first stellar generation. They were nothing like the stately, symmetric spirals and ellipticals that dominate the modern universe. They were the rough drafts, the first prototypes, the initial experiments in a process of assembly that would continue for billions of years. Of all the hundreds of billions of galaxies in the observable universe, one is special to us in a way that no other can be, not because it is the largest or the most luminous or the most ancient or the most structurally remarkable. It is special simply because it is ours, because the sun is one of its stars, because the earth is one of its planets, because every human being who has ever lived has spent their entire existence, from birth to death, inside it. The Milky Way galaxy is a large-barred spiral galaxy, approximately 100,000 light-years in diameter and perhaps 12,000 light-years thick at its central bulge. It contains somewhere between 100 and 400 billion stars, depending on the lower limit you use for what counts as a star. It has a supermassive black hole at its center, Sagittarius A star, containing approximately 4 million solar masses. It is surrounded by a halo of old stars and globular clusters extending to distances of hundreds of thousands of light years. And it is embedded in a dark matter halo that extends to perhaps 1 million light years and contains many times the mass of all the visible stars combined. The Milky Way formed, like all galaxies, from a merger and accretion of smaller protogalactic fragments during the first few billion years of the universe. Its oldest stars, found in the ancient globular clusters orbiting in the galactic halo, formed more than 13 billion years ago, less than a billion years after the Big Bang. The disk of the galaxy, the flat, rotating structure containing the spiral arms and most of the ongoing star formation, began to assemble perhaps 10 to 12 billion years ago. The Sun formed in one of these spiral arms approximately 4.5 billion years ago, condensing from a cloud of gas and dust that already bore the chemical enrichment of multiple previous generations of stars. The Sun is not a first-generation star. It is not even a second-generation star. It is a third-generation or later star, a product of the long chain of stellar births and deaths that preceded it, inheriting the heavy elements forged in the cores of stars that lived and died billions of years before a solar system existed. The carbon and oxygen and iron and calcium that make up your body were forged in stars that burned and died before the Sun was born, before the Earth existed, before any planet in our solar system had formed. You're the galaxy's product. The Milky Way built you over billions of years of stellar evolution and chemical enrichment from the raw materials of the Big Bang. For most of the history of observational astronomy, the earliest galaxies were beyond our reach. We could see galaxies at great distances, at great look-back times, glimpsing the universe as it was hundreds of millions or a few billion years ago. But the first galaxies, forming in the first few hundred million years after the Big Bang, were too distant, their light too thoroughly redshifted from visible into infrared wavelengths for any instrument we had built to observe them clearly. The James Webb Space Telescope changed that. Launched on Christmas Day 2021 and deployed to its operating location at the second Lagrange point, 1.5 million kilometers from Earth in the direction away from the Sun, Webb began science operations in mid-2022. Its primary mirror, 18 hexagonal gold-coated beryllium segments forming a combined aperture 6.5 meters across, is the largest space telescope mirror ever deployed. Its infrared detectors, operating at temperatures close to absolute zero and shielded from the warmth of the Sun and Earth by a 5-layer sun shield the size of a tennis court, are sensitive to the precise wavelengths at which the light of the earliest galaxies arrives at Earth. The images Webb has returned have astonished astronomers, not merely in their beauty, though they are beautiful beyond any previous standard of astronomical imaging, sharp and deep and alive with color and detail. They have astonished astronomers in their scientific content, in what they reveal about the early universe that no one fully expected. Webb has found galaxies existing less than 300 million years after the Big Bang. Galaxies at redshifts greater than 13, meaning their light has been stretched by a factor of more than 14 by the expansion of the universe during its journey to us. These galaxies are forming stars at rates and displaying brightnesses and showing structural features that challenge the standard model of galaxy formation in important and not yet fully resolved ways. The early universe, it appears, was more vigorous, more productive, more structurally advanced at early times than the models had predicted. Galaxies were assembling their mass more quickly, building their stellar populations faster, developing disk-like structures earlier than the simulation suggested was possible. The universe, in the first billion years, was more creative and more efficient than we had expected. What Webb is teaching us about the first galaxies is still being digested, still being incorporated into revised models, still generating debate and excitement and new theoretical proposals. We are, at this moment in the history of astronomy, in the middle of a revolution in our understanding of how the first structures in the universe formed. And that revolution is being driven by light that left its source more than 13 billion years ago, that has been traveling through the expanding cosmos since before the Sun existed, and that is only now, finally, arriving at an instrument sensitive enough to receive it. Let us step back now from the details of individual galaxies and their formation and try to take in the full scale of what the universe has assembled. The observable universe, the region of space from which light has had time to reach us in the age of the universe, contains an estimated 2 trillion galaxies. 2 trillion, 2 million, a number so large that if you tried to count them at the rate of 1 per second, it would take you 63,000 years to finish, roughly 10 times longer than all of recorded human history. 2 trillion galaxies, each one containing hundreds of billions of stars, each star potentially orbited by planets. Some of those planets potentially harboring chemistry complex enough to produce life. The numbers involved in even a conservative estimate of the total number of potentially habitable environments in the observable universe are so astronomically, so overwhelmingly large that the mind cannot hold them as anything other than abstractions. And yet each one of those 2 trillion galaxies began as a small, clumpy, irregular protogalactic fragment in the early universe. Each one assembled itself from the merger and accretion of smaller systems over billions of years. Each one is threaded through with the invisible scaffolding of dark matter that has been building since the Dark Ages. Each one hosts, at its center, a supermassive black hole whose mass is tightly correlated with the properties of the galaxy around it, suggesting a deep and not yet fully understood coevolutionary relationship between the black hole and the galaxy that grew around it. The universe is not a random scattering of galaxies. It is organized. The 2 trillion galaxies are not distributed uniformly through space. They are arranged in the cosmic web, in the filaments and sheets and nodes of the large-scale structure, whose seeds were planted by inflation and whose shape was determined by the distribution of dark matter. Galaxy clusters, containing hundreds or thousands of individual galaxies bound together by gravity, sit at the nodes of the web. Galaxy filaments, long chains of galaxies and galaxy groups, connect the clusters. And between the filaments, the enormous cosmic voids, regions of space hundreds of millions of light years across that contain almost no galaxies at all, occupy the majority of the universe's volume. This is the universe we inhabit. This is the architecture that gravity built from the seeds of the Big Bang. Over 13.8 billion years of expansion and cooling and collapse and merging and star formation and evolution. This is what the Big Bang became. And somewhere within it, orbiting an unremarkable star in an outer spiral arm of a large barred spiral galaxy in a modest galaxy group called the local group, on a small rocky planet whose surface is coated in liquid water and wrapped in a thin shell of nitrogen and oxygen and trace gases, you're lying in the dark, breathing slowly, your mind drifting towards sleep, made of the atoms of that Big Bang. The product of all of that history, the current endpoint of 13.8 billion years of cosmic creativity. You are the universe's way of looking at itself. And the view from where you are is extraordinary. We have been speaking all night about the universe we can see, about the photons that carry information across billions of light years, about the stars that emit them, about the galaxies that contain the stars, about the cosmic microwave background that carries the imprint of the early universe across 13 billion years of expanding space. We have been speaking about the 5%. 5%. That is the fraction of the total energy content of the universe that consists of ordinary matter. The atoms, the protons, neutrons, and electrons, the hydrogen and helium and carbon and iron and everything else on the periodic table. The stuff that stars are made of, and planets and oceans and living things. The stuff that you're made of. All of that, everything we have discussed, everything that emits or reflects or absorbs light, everything that makes the universe visible to any instrument we have ever built or imagined, is 5%. The other 95% is something else, something we cannot see, something we can only infer from its gravitational effects on the 5% we can observe, something that reveals itself only in the movement of stars within galaxies, in the bending of light around galaxy clusters, in the large-scale structure of the cosmic web, in the rate at which the universe expands. 27% of the universe's total energy content is dark matter. We know it exists because without it, the galaxies we observe would fly apart. The stars in the outer regions of spiral galaxies orbit their galactic centers at speeds far too high to be explained by the gravity of the visible matter alone. Something unseen is providing additional gravitational mass, holding the galaxies together, keeping the stars in their orbits. That something is dark matter. We do not know what it is. We have not directly detected any dark matter particle in any laboratory. It may be a new, as yet undiscovered type of fundamental particle that interacts with ordinary matter only through gravity and possibly the weak force. It may be something else entirely. It is one of the greatest unsolved mysteries in physics. And 68% is dark energy, an even stranger ingredient. Not matter at all, but a property of space itself, a latent energy embedded in the vacuum, perfectly uniform, perfectly constant, filling every cubic centimeter of space with the same energy density regardless of how much the universe has expanded. Dark energy is responsible for the accelerating expansion of the universe. The discovery, made in 1998, that the universe is not merely expanding, but expanding faster and faster with every passing billion years, driven apart by a repulsive energy that permeates the fabric of space-time. We understand dark energy even less than we understand dark matter. Einstein anticipated something like it when he introduced the cosmological constant into his equations of general relativity, then famously called it his greatest blunder when the expansion of the universe was discovered. It turns out his instinct was correct, though perhaps for reasons he never imagined. The cosmological constant is real. The vacuum has energy. Space itself pushes the cosmos apart. We live in a universe that is 95% invisible to us. We have charted the 5% with extraordinary precision. We have built civilizations and sciences and philosophies from our understanding of the 5%. And the other 95% moves quietly through our world, through our bodies, through our atoms, through the space between our thoughts, and we barely know it is there. The universe is far larger, far stranger, and far more full than it appears. And that, somehow, makes it more magnificent, not less. We have traveled tonight from the very beginning, from the question of nothing, through the Planck epoch and the grand unification transition and inflation and the quark-gluon plasma and the matter-antimatter asymmetry and Big Bang nucleosynthesis and recombination and the cosmic dark ages and the first stars and the first galaxies. We have traced the story of the universe from its first fraction of a second to the present. But every story has an ending. And the universe, for all its vastness, for all its apparent permanence from the brief vantage point of a human lifetime, is not exempt from this. The universe has a future, a long future, almost incomprehensibly long, but finite. And the physics we have learned tonight allows us to trace that future with reasonable confidence, at least in its broad outlines. In the short term, cosmically speaking, the universe will continue much as it is now. Stars will form and burn and die. Galaxies will merge and evolve. The cosmic web will continue to be drawn together by gravity along its filaments and into its nodes, while the void between the filaments grow ever larger as dark energy accelerates the expansion of space. In approximately 4 billion years, the Milky Way and Andromeda will begin their collision. Over the course of hundreds of millions of years, they will merge into a single large elliptical galaxy, sometimes called Milkomeda in popular accounts, a new island in the cosmos assembled from the two islands we know. The Sun will survive this merger, most likely flung into a new orbit within the merged galaxy, but not destroyed. Long before the merger is complete, however, the Sun will have exhausted its hydrogen fuel, swelled into a red giant, and rendered the Earth uninhabitable. But that is a story for another night. Further in the future, in roughly 100 trillion years, the last stars will burn out. The smallest, most frugal red dwarf stars, burning their hydrogen so slowly and so carefully that they can sustain fusion for 100 times longer than the current age of the universe, will finally exhaust their fuel and fade to cold, dark, inert cinders. The universe will be a collection of stellar remnants, white dwarfs and neutron stars and black holes, drifting through an expanding cosmos with no new fires to replace the ones that have gone out. Then, in the incomprehensibly distant future, even the remnants will fade. Protons may decay, if the theories that predict this are correct, dissolving the atoms of the white dwarfs and neutron stars into radiation and leptons over timescales of 10 to the 36th years and beyond. The black holes will evaporate through Hawking radiation, over timescales so vast that the current age of the universe is a rounding error by comparison. And eventually, if current physics is correct, the universe will reach a state called the heat death, a condition of maximum entropy, maximum disorder, in which no further thermodynamic work is possible. No temperature differences remain to drive any process. No information is organized into any structure, and the universe is a cold, dark, expanding, featureless sea of photons and leptons and the faintest possible radiation, approaching absolute zero as the expansion continues forever. That is one possible end. There are others. The dark energy could change in character over cosmic time, growing stronger and eventually tearing apart galaxies, then stars, then planets, then atoms themselves in an event called the Big Rip. Or the dark energy could reverse sign, eventually slowing the expansion and causing the universe to recollapse in a big crunch. These alternatives are currently considered less likely than the heat death scenario given the observational evidence, but they are not ruled out. Whatever the end, it is very far away, and between now and then, the universe has an enormous amount of history still to make, stars still to burn, galaxies still to merge. Perhaps on some of the hundreds of billions of potentially habitable planets that the current generation of stars will eventually produce, life still to arise, and minds still to look up at the night sky and wonder, as you are wondering now, where it all came from and where it is all going. The universe began in fire. It will end in cold, and between the fire and the cold, there is us. We have reached the end of our journey tonight. We have traveled together from the question of nothing to the architecture of everything, from the blank time to the far future, from the first fraction of a second, when the universe was a featureless plasma of unimaginable energy, to the present moment, in which you lie in the dark with the accumulated history of 13.8 billion years of cosmic creativity woven into every atom of your body. I want to close not with physics, but with a feeling, with the quiet, profound, oddly comforting feeling that comes from truly sitting with this story, not as an abstract account of events in the distant past, but as a personal history. Your personal history, the history of the matter that makes you, and the forces that organized it, and the time that allowed it to become what you are. You are made of Big Bang hydrogen and helium. You are made of the heavy elements forged in dying stars. You are made of the specific arrangement of atoms that 4.5 billion years of solar system chemistry and 4 billion years of biological evolution on this particular rocky planet produced in this particular lineage, leading to this particular moment. The probability of you, specifically being here in this form, in this moment, is so vanishingly small that it cannot be meaningfully calculated. And yet here you are. The improbable happened. You exist. The universe did not know, when it began, that it would produce you. There was no blueprint. There was no intention. There was only the physics, the simple and deep and beautiful physics, playing out over time with the patient creativity that only unimaginable timescales can produce. The Big Bang did not aim at you, but it made you anyway through the long, branching, contingent chain of events that connects the first second to this one. That is not a small thing. The stars that forged the carbon in your cells burned for millions of years and died in catastrophic supernovae to scatter that carbon into the interstellar medium. The interstellar medium drifted through the galaxy for billions of years before it was gathered into the solar nebula. The solar nebula took millions of years to collapse into a sun and its planets. The Earth took 4.5 billion years to produce through the slow engine of biological evolution, a creature capable of lying in the dark and listening to this story. All of that happened so that you could be here. Not purposefully, not by design, but consequentially, causally, physically. You are the consequence of everything. The current end of a chain of causes that began with the Big Bang and has not stopped running since. And tomorrow, when you wake, when the ordinary world reasserts itself with its demands and its schedules and its particular human weight, perhaps you will carry a small piece of tonight with you. Perhaps you will remember, for a moment, that the cup in your hand is made of stellar ash, that the air you breathe was exhaled by ancient seas, that the light coming through the window traveled 8 minutes from a nuclear furnace forged from Big Bang hydrogen, that you are, in the deepest and most literal sense, a child of the universe, assembled from its oldest ingredients, powered by its processes, thinking its thoughts. You came from the Big Bang. You're the Big Bang thinking about itself. And that is extraordinary. Quietly, personally, intimately extraordinary. Not in a way that requires you to do anything with it, or to tell anyone, or to change any plans. Just in the way that a true thing is extraordinary when you sit with it long enough in the dark to really feel it. The universe is 13.8 billion years old. It took all of that time to make you. And tonight, for 3 hours, you let it tell you how. Sleep well. The universe will still be here in the morning. It always is.